Hello, hello. Chengxi, can you hear me? Hello, hello. Chengxi, can you say something? Make sure I can hear you.
Yes. Hi, everyone. Oh.
There's echoes, right?
Yes, yes.
You also hear echo on your side? It's probably you. Can you hear
Maybe
me?
I should mute the web portal.
Yeah, you just open. I mean, use one microphone. That should be okay.
Hello?
There's still echo. Let me see if it is on my side. But I think I just logging with one account. I see the two of you. You have both the KDD Zoom 15 and also Chengxi Zhang as a guest, right?
What about right now?
Now it's good.
Okay.
Now it's good.
So I just closed the online web portal. So
Okay.
hi, everyone. This is the KDD 2020 tutorial, Recent Advances on Graph Analytics and its Applications in Healthcare. The tutorial will start in 8 a.m.
Should we also send all the information in the VFairs conference chatting room? Did you send out the information there?
Yeah, give me a few seconds. Let me check it.
Okay.
Hi, Fei.
Yeah, I'm here.
Oh, yes. Can you see? I just post all the informations in the Wayfire's chat booth.
Yeah, I saw that.
Okay.
Very good. So do we want? Oh, I'm sorry. It's on my side. So it seems we cannot open both Zoom and Hoover. So do we want people to ask a question on Zoom chat window or on Hoover or on vFairs? I think we have 3 places. Chanxi, did you hear me?
Oh, yes. I think Zoom and Wova are preferred.
But you cannot open both Zoom and Hoover. I think if you don't speak, that's fine. But
Yeah,
for us, I think.
I can just mute it and collect the questions.
Okay.
Hi, Faith. Can you hear me? We think Fei, Yangqiu, and me are on board right now. We have 3 hosts right now. Hi, everyone. Just a test of sound. Can everyone hear us clearly? Also, please kindly refer to this webpage for the detailed outlines and related materials of this tutorial. Oh, thanks for your response. So someone said yes. All right. Oh, as for recording this conference, the KDD community has already set the default record. They record this conference tutorial by default. And after the tutorial, we will ask the KDD committee to ask for the video. Thanks. Also, this tutorial is a live streaming tutorial. Also, after that, we have uploaded all the videos to the YouTube. Please refer to our webpage for the videos afterwards. Hi, everyone. Shall we begin? Hai Fei, Yang Qiu, Jian Pei. Shall we begin?
Yeah, sure,
All
I
right.
think we can.
Hi, everyone. This is the KDD 2020 tutorial, Recent Advances on Graph Analytics and its Applications in Healthcare. Thanks for your coming. Also, thanks for the speakers and the curators, Professor Fei Wang from Cornell University, Will Cornell Medicine, Peng Cui from Tsinghua University, Beijing, Jian Pei from Simon Fraser University, Canada, Yangqiu Song from the Hong Kong University of Science and Technology, and the last, Chen Xizhang, so it's me, also from the Will Cornell Medicine, Cornell University. Please kindly refer to this webpage for all the informations, the slides, the videos, and the detailed outlines of this tutorial. Here is the brief outline of this tutorial. We will begin by introducing this tutorial by Professor Jian Pei.
morning.
Give me a few seconds.
Good morning, good afternoon, or good evening, depending on where you are. Welcome to our KDD 2020 tutorial on recent advances in graph analytics and its applications in healthcare. This tutorial will be given by 5 of us. Professor Fei Wang is from Cornell University. Professor Peng Cui is from Tsinghua University. This is Jen Pei from Simon Fraser University. Professor Yang Chiu Song is from the Hong Kong University of Science and Technology. And Dr. Chengxi Zhang is also from Cornell University. In this tutorial, we'll cover 5 different sections. I'm talking about the introduction section, and the rest 4 sections will be taught by our other presenters. Well, let's start from the application. Long time ago, for medical applications, our dream is that we can have one magic medicine. It is one size fits all design. Hopefully, for one disease, we use one medicine and can cure the patients. However, this is unrealistic and also impractical. In order to achieve precision medicine, we need to be diverse. We need to give different patients different medicines. This is a strong transition from the one-size-fits-all to precision medicine. It needs multiple-level patient stratification. In order to implement this stratified medicine and precision medicine, we need to understand the patients, we need to understand the medicine, we need to understand the process of fighting against diseases. Therefore, we need a lot of data. The precision medicine tries to ensure the delivery of the right intervention to the right patient at the right time. In an article a few years ago named A New Initiative on Precision Medicine, the author said the initiative will encourage and support the next generation of scientists to develop creative new approaches for detecting, measuring, and analyzing a wide range of biomedical information. These would include molecular, genomic, cellular, clinical, behavior, physiological, and environmental parameters. As you can see, in order to achieve the precision medicine, we need a lot of data. We need a lot of data from many different sources and for many different purposes. Precision medicine is well beyond the inflection point. Indeed, we need a lot of different data to connect together to get a better understanding about the cause of the problems, or the cause of the disease, and the spreading of the disease and the patients. And that's another article on this subject. Let's look at different kinds of data that may likely be useful for precision medicine. First, you may think about the electronic health records, EHR. Electronic health record is an evolving concept defined as a systematic collection of electronic health information about individual patients or populations. It is so important for our medical purpose. But at the same time, electronic health records are highly distributed in different locations. For example, different hospitals, different practitioners. And it is so hard to connect them together. Even for one patient, it is a great challenge to collect all the related technical records, healthcare records, and put them in the electronic way. We see a lot of AI research, data mining research on medical imaging. Indeed, there are different kinds of medical images. For example, we may have X-ray computed tomographic. We may have precision emission tomographic. We may have magnetic resonance imaging. And different medical images may need a different processing, and they are also need to be connected to each other. Therefore, even we mention the simple term of medical imaging, we still need to collect them, connect them, and then working on them to make sense from the medical images. Drugs are important for medical. Drugs are typical chemical compounds. However, there are many different designs of drugs, and we need to understand how drugs take effect for patients. And this needs a lot of data. To understand deeper into patients and the medicines and also the diseases, we may need to look at gene data. These may include the DNA data, the gene data, the gene expression, for example. If we want to put drugs, medicine in action, and we look at the whole process, then we come to the physiology data. Physiology is the scientific study of function in living systems. It is a subdiscipline of biology. Physiology focuses on how organisms, organ systems, organs, cells, and biomolecules carry out the chemical or physical functions that exist in a living system. In other words, physiology is about the science of a dynamic system. And of course, in order to understand such a dynamic system, we need a lot of data. And we need to analyze a lot of data. Medicine or medical process, in large, is a communication process. Therefore, the patient's interaction is critical. We conduct all kinds of different patient surveys in the medical process. Therefore, understanding the patient survey data and making good sense of such survey data is important. So patient survey is another important kind of data that is needed in the healthcare process. Social media. Social media is so important, and we all know that in our current pandemic. Social media can carry information and misinformation, and it connects patients, health people, care providers, and many different parties. There are general social medias like Facebook, Twitter, LinkedIn, and so on. There are also some specific social media connecting patients and their care providers, for example. Social media produces a lot of data that are useful for healthcare. Environment. Many diseases are related to environment. Therefore, collecting environmental data is important. So, collecting environmental data is far from trivial. And also, we need to collect different data sources and make good sense of such data. Medical researchers have produced a large amount of biomedical literature. Therefore, it is important for us to search and extract useful information and knowledge from biomedical literature. So, biomedical literature is another important kind of data sources that we need to rely on in healthcare. We have so many different data sources. How can we put them together and make good use? A natural way to put them together is to form a network or a graph. Graph is almost the last resort we can use when we are facing complicated data sources and complicated information. Because graph also represents the divide and conquer methodology in our scientific research. Why is a divide and conquer? Because in a graph, we have nodes and edges. Within a local region like an edge or a node, then you can see that it is more or less structured. However, graph can also allow us to model globally unstructured information. Therefore, graph is a very natural and useful structure for healthcare data. As you can see, we have a large graph. For example, even in this pandemic period, we can use the graph to organize the related information to understand the development of drugs quickly. This is the WHO figure about the pandemic situation. Here you can see we can connect the confirmed cases and the regions and also the countries. And also, graph data can help us to find drug repurposing. And in this, in a recent study in cell discovery, they used network-based data to help the drug repurposing for the novel coronavirus 19. So you can see graph and network data can help us to integrate information from different sources and then can help us to go through a complicated, a sophisticated process of drug development. Moreover, using graph data, we can form a knowledge graph. And using the knowledge graph, we can conduct a very useful and helpful services to patients and medical workers. For example, question answering and decision support. Patients and medical workers can ask questions, and the search engine can automatically discover the answer from knowledge graphs. And also, knowledge graph can provide useful information to support the decisions made by medical workers. There are more applications in healthcare using network data. For example, in silico drug molecule design, and it helps us to understand the pros and cons of different drug designs and how to filter out those unpromising designs. So in this introduction, I hope I can motivate you to very broad and meaningful application of network in connecting different sources, serving the healthcare applications. In the rest of this tutorial, we will explain how those data sources can be integrated using network and how the network can be analyzed and mined to derive useful knowledge for medical domain. Thank you.
Hello, everyone. Welcome to this tutorial. I'm Peng Cui from Tsinghua University. I will deliver the second part on the network embedding and also graph neural networks. As introduced in the first part, actually healthcare is closely related with graphs because many healthcare problems can be modeled as graph problems. Like drug retargeting, you have a lot of drugs, you have a lot of diseases, and also a lot of drug ingredients. And you can represent all of these entities into a network. And then if you want to predict a link between a drug and also a diseases, then this is actually a drug retargeting problem, right? And also in the adverse drug reaction problem, you have a lot of drugs, patients, and also their adverse effects. Then you can represent this into a graph, and then you can predict the links between the adverse effect and also a drug and also a patient. Maybe this is a hypernetwork problem, right? So we can see that a lot of this kind of healthcare problem can be transformed into graph problems. But unfortunately, network actually is quite challenging to be analyzed. I think maybe one fundamental problem is it's not very learning friendly because a lot of other data formats like text, like video, image, they can actually represented by some forms of vectors. And then you can input this kind of feature vectors into the off-the-shelf learning models to solve the problems in this kind of domains. But in the networks, because networks are full of these kind of links, right? And then this make the graph actually a topological structure. And topological structure actually is not easy to be represented by vectors. Of course, you can represent a graph into vectors like a adjacency matrix, but this is a very high dimensional and very sparse vectors. So they are not very friendly to the off-the-shelf machine learning methods. So that's why actually in the data mining and also machine learning literature, there is another pipeline of research for the network data. So for network data, we usually need to manually extract some features, right? And then we discover some patterns in the extracted feature space. And then we just try to apply this kind of patterns into the network applications. So I will just give you an example. If you find that in this network, this yellow nodes, actually there are some special nodes, maybe some abnormal nodes. So how can we just identify whether there are some other nodes that are also abnormal, right? So actually this is, I would say this is a learning problem, right? So this kind of yellow nodes are actually the supervised information. So you can build up a learning model and then you input other models into the nodes into the learning model, and the model should predict whether this is a normal or abnormal nodes, right? So this is actually a learning problem. But because most of the learning models, they are designed for vectors, and as I said, it's not easy to represent the network nodes into the vectors. So we need this kind of pipeline, right? So we need to manually observe, okay, what kind of features that is common for these 3 nodes. And then we just extract this kind of features. And then we just use these features to identify whether other nodes are normal or abnormal, right? So this, a lot of human efforts actually involved in this whole process. So we say that, okay, network actually confronts some challenges in the learnability problem, right? Okay, so in order to solve this kind of problem, in order to provide a general and also scalable solution for network problems, okay, there are 2 lines of research. And these 2 lines of research are actually, the target is try to solve the problem of learning from networks. So one line is network embedding, and the other line is just the graph neural networks, okay? So in this part, I will just try to introduce the recent progress in these 2 lines and also try to differentiate these 2 lines of research in different contexts. So firstly is a network embedding. You know, network embedding actually is a quite natural and straightforward solution for learning from networks. As I just discussed, the major problem for network is vector representation problem, right? So whether you can, if you can transform the network into a good vector representation, then of course we can use off-the-shelf machine learning methods to deal with the networks, right? So the network embedding is just doing this, okay? And more intrinsically in the network embedding, there is another, there is a hypothesis that, okay, network actually is just the appearance. So what kind of data actually they generate this kind of appearance? Like in the social networks. So 2 persons, they form a link, right? So why they form a link? There must be some maybe similarity or proximity between these 2 persons. Maybe they're classmates, maybe they have similar preferences, right? And they need some proximity to form a link, right? So in this way, we can think that, okay, maybe there is a latent vector space, because if you just want to reflect the proximity, maybe vector space is the most straightforward way to represent that, right? So there may be a latent vector space. Actually, they generate this kind of network structure, right? But the problem is we cannot observe this kind of latent vector space, right? What we can observe is just this network structure. So the problem is whether we can embed this observed networking structure back into the latent vector space, right? So if we can do that, then all of the links actually disappear. They are replaced by the distance metric in the vector space, right? And then we can complete the process of transforming the topological structure into the vector space, and then we can apply the classical machine learning methods to deal with the network data. Right, so I think this is the largest motivation for the network embedding. So of course, the network embedding is not just try to transform the representation space, but also we want to set a higher goal, that is whether we can support the network inference tasks in the form vector space, right? Because there is, actually is the intrinsic problem of network embedding is transform the topology into the vector space. So they are totally 2 different spaces, right? So in order to support the topological inference in this kind of vector space, we need to 2 constraints or 2 goals. One is that whether we can use this kind of latent vector space to reflect or to preserve the network topological structure. And the topological structure actually is not that simple as described in the network structure, the node, and the link. But there are a rich body of network structures that need to be reflected in the latent space, in the vector space, like a high order proximity, and also the community structure and something like that. And if we can preserve or reflect this kind of network structure in the latent space, that means in the information volume is just equal in the two spaces, right? And then it's possible to do network analysis tasks in the representation in the latent vector space, okay? And the other goal is we may also need to maintain the topological properties, because if you want to do some inference in the networks, then it should follow the topological properties, right? But now we have transformed the topology into the vector space. That means if you want to make inference in the latent vector space, you need to preserve some important network or topological properties in the latent space, right? So if we can accomplish these two goals, then we can guarantee maybe the vector space is able to support the network inference, right? So intrinsically, we think that the network embedding is just a transform the network nodes into vectors that are fit for off-the-shelf machine learning models. Right? So this is actually, I think, the basic idea for the network embedding research. And for the graph neural network, actually, they go to another way, because they are not trying to transform the network into a learning-friendly space, but they try to design a specific learning mechanism on the graph. Okay, so the network embedding is adapt network into the current learning framework, but the graph neural networks actually they design a specific learning framework for graph. Okay, so this is actually a big difference. For the graph neural network, actually the basic idea is just a recursive definition of states. That means a state of a node, actually they rely or they will be influenced by its own state, current state, or the state of the last time slice, and the states of its neighbors, and its own features, and the features of its neighbors, and also the connection structure between the node and its neighborhoods. Okay, so this is actually, we can see this is a recursive definition of the states. But I would say that this kind of recursive definition is quite common in the graph study literature, right? And a very simple example is just the PageRank, right? So the PageRank algorithm, the PageRank score of a node actually depend on its current score, its neighbor's score, right? And its connection structure between the nodes and other neighborhood nodes, right? So we would say that the learning mechanism actually is not new in the graph literature. And the main idea actually is just doing some message passing between pairs of nodes and aggregate all of the states of the neighboring nodes. So this is the function for one layer. That means, okay, for the L+1 layer states, the node states, it depends on the else layer states, and also these states will be smoothed by the agency structure, right? So this is A here is the agency matrix of the network. And that means in each layer, we're just doing some smoothing by the agency matrix, and then we conduct a transformation parameter here, and then we pass nonlinear stimulation function. And after stacking multiple layers like standard CNN, we can form the basic pipeline of the graph convolution neural network. Okay, so this is actually the main idea of the graph neural network. So if we just compare the network embedding and the GCN, their pipeline and their target, actually I would say there are some difference. So for the network embedding, you can see that given a graph, we just doing some network embedding to transform them into an embedding space. And then in this line, actually there is no supervised information. There is no task. We just want to transform the graph topology into this embedding space, right? And if you have a task, then you can just add on another task specific. For example, you have a classification task, then you can learn a classification model, right? Based on the embedding space, right? And if you have a regression task, you can learn a regression model based on the embedding space, right? And of course, in this process, I think the most important problem is how to transform the topology into the vector space. And in a lot of tasks, in a lot of scenarios, you have some node features, and then you can combine or just directly concatenate this kind of feature with the topological embeddings, and then you can train a task-specific model here, right? So you can see that this is actually from the input graph to the output embedding space. Actually, this is an unsupervised pipeline, right? And for the GCN, actually, especially in the initial stage, GCN was proposed as a good fusion framework for both the node feature and also the topology. So the input of the GCN is a graph structure and also the feature space and the node features. And then after a GCN, you can come out some task results. Okay, that means when we train the GCN model, actually we need to bring in some task supervised information. So basically, the network embedding, they're solving the problem of a topology to vector. But for the GCN, they are solve the problem of a fusion of topology and the features. And also, in some sense, the network embedding actually is a unsupervised pipeline. But for the GCN is a semi-supervised pipeline because the learning process actually is guided by the task supervised information. Okay, so from very high level, we can see the difference of network embedding and the GCN. And then I will just introduce some representative works in the network embedding and also the GCN and also the latest research trends in this two line of research. Okay. First is the network embedding. So as I just mentioned, that the intrinsic problem that network embedding is solving is just reducing the representation dimensionality while preserving necessary topological structures and also the properties. So why we say that this is actually a dimension reduction, because you can assume that a adjacency matrix of a graph actually is a vector representation, right? For each node, if we have n nodes in the graph, then each node can be represented by a neighborhood vector, right? And the dimensionality of the neighborhood vector is just n, right? So this is actually a very high dimensional and a very sparse vector representation. Of course, we know this kind of representation space is not good. So whether we can reduce the representation space into a low dimensional space, but at the same time, we can effectively preserve the necessary topological structures and the properties in the low dimensional space. Okay. So for the structures, there are a lot of research on how to preserve the node and the link structure, how to preserve the node neighborhood, how to preserve the pairwise proximity, and also some more complicated structures like community structures, hyper edges, and also the global structural role of a node, something like that, right? And there are a lot of research along this line. And also, we need to preserve some topological properties. And to mention a few, just like the transitivity, non-transitivity property in the networks, and also asymmetric transitivity, right? And also some uncertainties, dynamic characteristics, and also heterogeneity, interpretability. This kind of properties, how can we preserve them in the topological space, in the vector space? Right? So this is actually, I think, is the development logic of recent years network embedding research. Okay, so here I just, because of the time limit, I just introduced two interesting network embedding research in this line. One is just how to preserve the high order proximity and also the arbitrary order proximity. I think there is a consensus that in the network embedding research that high order proximity actually is quite important for network embedding. So here the high order proximity means that this is a network, and if you just consider the first order proximity, that means you just consider the nodes direct link. Okay, so that means only the nodes that are directly linked, okay, you will have some similarity constraint on their embedding vectors. Okay, but in the networks, actually, the proximities are quite complicated. So maybe these two nodes, okay, these two nodes are not directly connected, but they have some common neighbors. And this kind of common neighbors can tell some proximity between these two nodes. Okay, so this is actually the second order proximity. And also you can also consider the third order, like neighbors of neighbors, and the first order, the neighbors of neighbors of neighbors, right? And the higher order that you considered, the more constraint you can get for the similarity between any pair of nodes in the embedding space, right? But the problem is, okay, given a network and given a specific task, how much order that you need to consider in the network embedding process? Okay, actually, this is quite a critical problem. Sometimes you need, for example, you consider the higher order than sufficient. Actually, this information will play some negative role in the inference tasks, right? And sometimes if you just consider the orders that are insufficient for the task, then your embedding will be suboptimal, right? But the problem is, given a task, given a network, we cannot know what's the right order that we need to consider, right? Okay, so that's why, and that's a problem. That's why we need to investigate the arbitrary order proximity preservation in the network embedding. Okay, so this is actually in the KDD 2018, we proposed a solution for this problem. Just for network, we just need to run one parse network embedding algorithm, but this result can be shifted into different orders. That means we only need to run one parse algorithm, and we can generate the embedding vectors for the first order proximity, the second order proximity, the third order, the fourth order, and any order, arbitrary order, can be inferred from these embedding results. If we can preserve this kind of arbitrary order proximity, then you will just have a very low marginal cost to shift among different orders. And then especially for very large scale networks, and then you have this kind of flexibility to find out the optimal order proximity that you need to consider and preserve in the network embedding. So here I just introduced a general formulation of the problem. First, you need a formulation on the high order proximity matrix. So here we just use a polynomial function of the agency matrix, right? So if you just consider the first order matrix, first order proximity, then it's just the agency matrix, right? And if you need to consider second order proximity, then it's just can be represented by A squared, right? And so on and so forth. So we can give a general form of high order proximity matrix, this S, and actually this is a polynomial function of A, right? Okay, so if you can get this high order proximity matrix, of course we can directly use some matrix factorization methods to get the low dimensional embedding, like applying the SVD on the S, then you can get the, for example, you just use the top K eigenvectors, and then you can get the, K dimensional embedding vector for the network. But the problem here is for very large scale network, actually you cannot explicitly get or calculate the S, because for very large scale network, even the A square, you cannot calculate it, right? So this is one problem. The other problem is for very large scale network, even though you have the S, actually you cannot apply very efficient SVD, for example, on a very dense, very large scale matrix on the S. Because if you consider the high order proximity, then the S will never be a dense, a sparse matrix. It will be very dense. Okay, so in a very large scale dense matrix, you cannot run efficiently on the SVD model. Okay, so this is actually infeasible to directly to deliver the result. Now, after a very long period of research, we just find out quite a good theorem, that is eigen decomposition reweighting. So this theorem actually tells us that if lambda x, this is an eigenpair of A, then the f lambda x is an eigenpair of S in the polynomial function of A. Okay, so you can see that the x, so the eigenvector of A and Fa, their eigenvector actually are the same. The only difference is on the eigenvalue. But the eigenvalue actually can be directly derived. For the S, we can directly derive the eigenvalue for S by input the lambda, that means the eigenvalue of A, into the polynomial function. Okay, so you can see that we can derive the eigenpair of S in a very efficient way if you have got the eigenpair for the matrix of A. And for the matrix of A, actually this is a very sparse matrix, so we can efficiently run SVD on A to get the eigenpair, right? So you can see that in the traditional parse, for very large scale network, you have the adjacent matrix, then it's very, very, very time consuming to calculate the S, right? As I just mentioned. So this is actually infeasible. Even though you get the S, it's also very time consuming to run SVD on the S, right? So this step also infeasible. But if under the support of this theorem, we can run another parse. The parse is, first we can calculate the SVD result on the A to get the eigenpair for A, right? This is actually very efficient because A is very, very sparse. And then we just can input the lambda into the polynomial function of the S, and then we can get the f lambda and x. That is the eigenpair for the S. Okay, so also this step is very efficient, right? It's just some polynomial calculation on the values. Okay, so here you can see with this theorem, actually we can solve this problem with theoretical guarantee. I think this is a quite good solution for the arbitrary order proximity problem. Okay, so here I just show you some experimental results. In a lot of baseline network embedding models, actually the order of proximity are just fixed. For example, in line, you can just consider the first and the second order, and in the SDNE, it's just the second order. And their order of proximity cannot be tuned. Even in the deep work, of course, you can implicitly control the order by the random walk pass, the length of the random walk pass. But you need to rerun the deep work model if you just change the walk length, right? But for the rope, just the model proposed in this paper, we don't need to rerun the model, right? We just need to run the model one path, and you can get, okay, arbitrary order proximity result. So here you can see that, especially in very large scale networks, actually we cannot support to tune this kind of, for example, the walk length, this kind of hyperparameters. So I would say that the existing method, they cannot provide the flexibility to tune the order of proximity. So with this flexibility, so you can see that in a lot of data sets and also in different tasks, you have the flexibility to get the optimal order of proximity. Then you can get a very significant improvement in the performance, even one time or two times. So this actually can tell the importance of the flexibility to consider different order of proximities in network embedding. Okay, so this is one work I want to introduce. The other one is quite related to the healthcare network. That is a hypernetwork embedding. So hypernetwork, we know that in the common or simple networks, we just consider the node and the link. And the link, actually, they reflect the pairwise relationships between a pair of nodes, right? But sometimes we need to consider more complicated relationships. For example, you just need to consider the relationships of these three nodes, right? And three nodes, they form an edge. And this edge, actually, we call them the hyper edge. And the network with these hyper edges are called a hypernetwork, okay? So in a lot of scenarios, actually, we need this kind of hypernetworks to formulate the problem. For example, the adverse drug network, right? A person take a drug and then have a reaction. Actually, this is one fact, and this is one relationship, right? So we need this kind of hyper edge to reflect this or to formulate this kind of relationship. And usually we say that this kind of hyper edges are often indecomposable. Okay, so that means because in the graph research literature, one common way to solve this kind of hypernetwork problem is just try to transform a hypernetwork into a pairwise network. Okay, but we say that in a lot of scenarios, applications like healthcare, maybe the hyper edges are not indecomposable. For example, you have the person take a drug and have the reaction. You cannot transform them into the person and the reaction, the person and the drug and with the reaction. So this kind of pairwise relationships, right? This is not reasonable because you cannot establish a relationship between the person and the reaction. The person has a reaction only in the condition of taking this kind of drugs. Okay, so this is actually an indecomposable relationship. Okay, so the problem is how can we just embody this kind of indecomposable hyper edges into the network embedding space, into the vector space, right? So this is actually a quite challenging task. So we just propose this kind of structured deep embedding methods for neural networks. And the basic idea is, okay, you have different types for the nodes. For example, you have node type A, type B, and type C. And for each kind of node, of course, you can learn their latent representations by something like an autoencoder structure, right? You just learn their latent representations. But how can you just reflect their indecomposable relationships, right? So here we just design a triple-wise similarity function. And this similarity function actually is defined on a triple. That means only you input the latent representation of the node A and node type B and node type C, and then this similarity function will report, okay, it's 1 or -1. 1 means there is a hyperedge among these 3 nodes, okay? And -1 means there is no hyperedge between these 3 nodes. So you can see that with this kind of triple-wise similarity function, we can guarantee the indecomposability, right? So only you input these 3 nodes, you can get, okay, the similarity value, okay? So with this actually kind of indecomposable assumption, we can model the hyperrelationship among the nodes more accurately, okay? So here you can see that the difference. We just use the different, the existing methods for dealing with the hypernetworks to transform them into the pairwise relationships. And then you can use the pairwise relationship network embedding methods to deal with them, like the deep walk, the line, the node vect, and also some other baselines. And so here you can see that we use indecomposable hypernetwork embedding methods. We can get a very significant, improvement in the performance, okay, in their hyperlink prediction task. So here you can see this is a drug reaction data set, and we can improve the performance from 70 to 92. This is a very significant improvement. Okay, so here you can see that if the application scenario, they require this kind of indecomposable hypothesis, or they have a very strong assumption in this property, then this kind of assumption need to be embodied into the network embedding methods, and then you can get a much better result in the end application, okay? So this is actually the 2 works in the network embedding that I want to mention. And then I will just shift to the graph convolution neural network, okay? I'll say the intrinsic problem that GCN is solving, actually I just mentioned, is just a fuse topology and the features in the way of smoothing the features with the assistant of topology. Okay, so here you can see that the DAD actually means the topological structure. Okay, the H0 actually means the features. Okay, and the HL means the else states of all of the nodes, and then it's initialized by the feature vectors. Right. So here you can see that when we just using this kind of operation, a mathematical operation on this matrices, actually we can physically interpret that you are using the topological structure to smooth this feature space, right? So this is actually the very straightforward interpretation on the GCN. And in the recent years, I think there are some new trends in the GCN research. One is how to guarantee the robustness of the GCN, and there are a lot of research that tell that GCN actually is quite fragile, and if you just attack the GCN structure network with some noise, they are just a very not very robust in the final performance. So very small perturbations in the graph structures and node attributes will influence, significantly affect the results right? So a very important problem is how to improve the robustness of the graph convolution networks, right? And in last year's KDD, actually, we proposed a method on the robust graph convolution network against the adversary attacks. And the basic idea is in the traditional graph neural networks and also in the traditional network embedding, we tend to use just embedding a vector to represent one node, right? And this actually will make that, okay, if you have a noisy link and this noise will be taken to the embedding vector, right? But in this model, actually, we replace the vector representation with a distribution representation. That means for each node, we represent the node with, for example, Gaussian distribution. And the Gaussian distribution can be formulated into the mean vector and also the variance vector, right? And in this process, the variance terms, the variance vectors, actually they can absorb the effects of the adversary attacks, just like the noises, right? And also we are designing a variance-based attention mechanism. That means when you define the weights among the neighborhood structure, for example, how important is a node for the targeting node, right? And the weight actually is determined or it's determined by the variance. That means if the node variance vector is very large, okay, that means there are a lot of uncertainties on the on its representation. Then we will reduce down its weight in doing the neighborhood aggregation. So with this kind of variance-based attention mechanism, we can just remedy the propagation of the adversary attacks. That means the noise cannot be propagated to influence other neighboring nodes representation, right? So with this kind of design to replace the vector-based representation with this kind of distribution-wise representation, we can effectively improve the robustness of a GCN model. So here you can see the performance, okay? So with the ratio of the noise edges increase, you can see this is the RGCN and this is the GCN and the GAT. So you can see that there is a very obvious margin. That means, okay, by introducing the distribution-wise representation into the GCN, we can see that the effectiveness of preventing this kind of adversary attacks, okay? And the second problem we are just interested in is the interpretability of the GCN, okay? So both in the GCN and the network embedding, a basic hypothesis is if two nodes, they are linked, then they will have similar representations, right? But actually this assumption is not that reasonable. For example, two people, they form a link, they are not totally similar. They may be just similar in one part, right? For example, they have similar preferences on the movies, but they may have different flavors in the clothing, in the fashion, right? So we think that when we try to learn the representation to represent this kind of relational structures, we need to disentangle the representation space, okay? So by disentangle the representation space, of course, we can improve the interpretability, and also we can improve the robustness, right? Because we can make these representations to not overreact to irrelevant factors, okay? So, of course, disentangled learning is quite popular and quite hot in other fields like computer vision and also in the NLP. But in the network, actually, it's not very easy to do this kind of disentanglement. So after a long period of research, we just think that, okay, in the graph structure, actually, this kind of, the dense local structures, like community structures, actually they are a very strong clue to tell the disentanglement. For example, this is a node neighborhood structure. Okay, so obviously its neighborhood actually they have some community structures. Okay, so the one assumption is one community structure actually should correspond to one disentangled factor, because the U actually just linked with this nodes, and these nodes are closely connected each other. That means they should follow the same disentangled factor, right? And the other community, they should follow another disentangled factor. So we'll say that this kind of community structures can give us information clue to disentangle the representation space. So we just introduced this kind of hypothesis into the disentangled representation learning and propose a disentangled GCN model. I will just skip the detail, and if you're interested, you can refer to the paper in last year's ICML. So this is a result. We just visualize the representation space. So you can see that in the traditional GCM, actually, this is a different dimension in the representation space. So you can see that their similarity are the holistic similarities, right? But in the disentangle GCM, actually the dimension, their similarities there are some local structures. That means two vectors, they are similar, just similar in one or two components, but not a holistic similarity. So with this structure, actually it's easier to interpret the latent space, and also it's improve the representation expressive power of a certain dimensional representation space. Okay, so this is a disentangle GCN. And also in the GCN, actually, there are some quite interesting questions in the recent 2 years. A lot of interesting research. One problem is that what if the targeting problem is topology driven? So as I just analyzed and mentioned, that GCN actually is smoothing the features, right? Using the topology to smooth the feature space. Of course, we say that this is quite important, especially when the feature space is not that complete and full of noise. And then you can use the topological feature to smooth the feature space, right? But if this kind of assumption and this kind of design is inevitably feature-driven, right? Just the structure only provides some auxiliary information for the feature smoothing and filtering. So when in the data set and in a task, when the feature plays a key role, because it's feature driven and exploits the topology just for the smoothing purpose. So in this kind of scenario, when the feature plays a key role, then the GNN will perform very good, right? But how about the contrary case? That means when the problem is just a topological driven, then how about the performance of GNN? So we just conduct a very simple experiment on a synthesized data. That is, we just use a stochastic block model to generate a graph. Okay, that means the graph is full of some community structures. Okay, and the label of a node actually is determined by the community index. That means the label is totally topological driven. Okay, and then we just assign some random features, okay, on the nodes. So in this kind of task, you can observe, you can guess that the feature actually they don't play any role in predicting the node labels, because the node label is just determined by the community structure. It's totally determined by the topology, and the features, they are just random features. Okay, so in this kind of setting, we just compare the random method, the GCN, and also the deep work, a very simple network embedding method. So this is a result on accuracy. So you can see that the GCN performance is just similar as a random guess. Okay, and very simple network embedding method, they can get performance, perfect performance. Okay, so that means, okay, the GCN, actually, the current GCN, actually, they have some limitation or serious problem in this kind of topology-driven tasks. Okay, so this is actually one problem that need to arouse our attention when we are adopting a GCN to perform a task. Okay. The second question is, does GCN fuse feature and the topology in an optimal way? I think from the previous slides, we can tell, of course, it's not optimal, right? Because they have the limitation in capturing the graph topological information, right? And of course, we can propose some methods, some variants of GCN model to capture, for example, to enhance their expressiveness on the graphical topology, network topology. But the other question is, given a task, given a data set, we can never know whether the task is topology driven or feature driven, right? So ideally, we need a model to be adaptive to different kinds of tasks and the data sets, right? So how can we design this kind of adaptation mechanism? Okay, so in this year's KDD, we have another method on the adaptive multi-channel graph convolution networks to adaptively to fuse the topology and the feature with any tasks and also data sets. Okay, so if you're interested, you can listen to the talk of this paper. And also in the last year's ICML, there is a very interesting paper that is simplifying graph convolution neural networks. They just ask a quite interesting question, that is GCN truly a deep learning method? Okay. Of course, we know that this is a normal definition of GNN formulation, right? And here there are some nonlinear operator here, and actually it's a nonlinear operator make the GCN quite complicated in optimization perspective, right? Then this work actually, they just doing a trial that how about removing the nonlinear component, right? Just formulates the GNN in this form without the nonlinear function. Okay. Then after stacking multiple layers and add the softmax classification, actually this is ultimate. The objective function. So in this objective function, you can see that the S is a adjacency matrix. Okay. The S power K actually is just the high order proximity matrix as we defined in the network embedding works. Okay. Then we multiply the H0. H0 is the feature vectors of all of the nodes, and then multiply the weighting parameters. Okay. So here you can just see that after we removing the nonlinear term, then the intrinsic problem that the SGN is doing is just using the high order proximity matrix to smooth the feature matrix. Okay, so this is actually the SGN, and this is the SGN. And very interesting is that in the result in the current benchmark data set, you can see that you just remove the nonlinear term and use a very simple idea, just to use a high order proximity matrix to smooth the feature space. You can see that the performance is just very comparable with the GAT and the GCN with the nonlinear terms. Okay, so actually this is quite interesting to investigate what's the necessary, whether it's quite important to introduce a nonlinearity into the graph learning problems, and whether there are some more simple and minimal model for the graph convolutional neural network structure. I think this is quite interesting to further investigate. Okay, so overall, I just want to say that the network embedding and the GCN, actually there are two pipelines, or there are two lines of research try to solve the problem of learning from networks. Right? One is just vectorize the topologies and use off-the-shelf machine learning methods to deal with network. And the other one is to design a specific learning mechanism on the graph topological structures, right? And from the previous comparisons, we can see that actually there is no absolute better one, but there is more proper one. If the data set actually is depend more on the topology, maybe network embedding methods, they can perform better because they have rich design in how to preserve different kinds of topological structures in the network embedding space, right? But if the task is quite not feature-driven, then you can just use a feature-based learning, right? For example, you just use NLP to do this kind of task. Because maybe if you introduce this kind of topological structure, they will just have some negative impact, right? And if the task is determined or driven by both the topology and the node features, okay, then the GCN actually is a right option, a better option to be adopted, okay? So I would say that I just want to summarize the network embedding and the GCN. One is for the unsupervised and one is for the semi-supervised settings. And one is the topology driven and the other is feature driven. Of course, in the healthcare, there is a very large spectrum of different healthcare tasks. So we need to just consider in this, given a certain healthcare task, okay, how do you select whether you just use a network embedding or whether you just use a GCN. Actually, we need quite a substantial understanding on their differences and also on their, the applicability in different kind of scenarios. Okay, so that's all for the tutorial, and questions are welcome. Okay. Finally, I'll just want to remind that we have, if you are interested in the network embedding part, you can refer to our recent survey on the network embedding. And if you are interested in the deep learning on graphs, just like the GCN, you can refer to our another survey in this line of research. Okay, thank you.
All right. So we just finished the first two parts. We just finished the first two parts, the introduction part and the network embedding part and the GNN part. So just feel free to propose any questions in our Zoom chatting Zoom, and we will collect the questions and we will select them to answer to propose the questions. So our next chapter is knowledge graph mining and healthcare and graph generative models and drug discoveries. And right now we have a half-hour break. So, which means, so we can feel free to take a break and feel free to leave any questions in the chatting room. So we will come back in half an hour. Thanks everyone, thanks for your coming. Hi, everyone. Again, this is the second part of the KDD 2020 tutorial, Recent Advances on Graph Analytics and its Applications in Healthcare. Please refer to this webpage for more details of this, for the slides, outlines, and videos, and so on and so forth. So in the second part, we will focus on knowledge graph mining and its applications in healthcare, graph generative models, and its applications in drug discoveries. And then we have enough time to discuss the more subtle issues. For example, the privacy, interpretabilities, bias, ethics, and so on and so forth with Professor Fei Wang. More information is in this webpage. So let's right now start the second part, knowledge graph mining.
Hello everyone, my name is Jiang Song. I come from Hong Kong University of Science and Technology. I will introduce the third part of the tutorial, which is about healthcare-related knowledge graph construction and inferences. I will first give a brief introduction to knowledge graphs, and then introduce how we're going to construct a knowledge graph and then make inferences using related machine learning techniques. So first of all, what is a knowledge graph? A knowledge graph may have different names. For example, semantic networks, knowledge base, or ontology. The term knowledge graph was officially used by Google in 2012. It has been used to support many search queries such as entity fact-checking and question answering. Here is an example of a search result with the query Anthony Fauci. On the right-hand side, Google Knowledge Graph returns some key attributes of this entity. Here's another example. When you search COVID-19, Google Knowledge Graph returns the key facts that are almost real-time updated. So here is a comparison of current state-of-the-art enterprise-level knowledge graphs. For example, as of 2019, Google has 1 billion nodes and 70 billion edges in its knowledge graph. Other giant companies also have similar scales. As you can see, not only search engines, but also recommender systems and social networks, they all have their own knowledge graphs. Google Knowledge Graph is also used in healthcare. For example, it has been used to support diagnosis decisions or checking symptoms. Like in Google Health, which was released in 2015, they demonstrated that the aggregated search result can formulate a healthcare-related knowledge graph. The knowledge graph can then be used to support multifaceted search. The Google Health Knowledge Graph has been carefully checked and reviewed by medical doctors and thus considered to be accurate for many diseases. Here is another example of knowledge graph about symptoms and diseases. The knowledge graph is constructed based on the Biomedical Literature database PubMed. As you can see from a subgraph on the left, two similar diseases have similar symptoms, but different symptoms have different weights that co-occur with the diseases. For example, both diseases are related to diarrhea, which is the most typical symptom here. But Crohn's disease is more related to edema and acute abdomen. While ulcerative colitis is more related to headache and constipation. So on the right-hand side of the figure, the graph of disease shows that the similarity actually reveals some interesting patterns of clusters. So the disease symptom network can be further used to analyze different kinds of disease similarities. For example, on the left, we construct the disease similarity based on symptoms. And on the right, we construct the similarity based on PPI networks. So the similarity can be based on either shared genes or first-order, second-order interactions. Then we can compare the two similarity networks. It's shown that they are highly correlated, but there are still some differences. We may be able to mine such disease symptom relationships or to mine more PP interactions based on this. Another example is to extract the symptom and disease relations from large-scale electronic health record. Here is an example where the biomedical concepts are detected from EHR data and then linked to an existing knowledge base to have a unique concept ID. And where the concept can be either symptoms and diseases. Then the concept patient relation matrix can be built to construct the symptom disease relations using some statistical models. So here I show two figures of the same two diseases. It's obvious that the relations detected from EHR are different from the ones extracted from PubMed literature. As EHR is more statistical, noisier than literature, some statistical models needed to be applied here. On the other hand, PubMed is more likely to be formal articles written by researchers, so they tend to only mention typical symptoms to promote learning. Here I show the precision recall graph of the extracted symptom disease relations examined by medical doctors to give you some sense about the results. The Google Health Knowledge Graph shows very high precision for both most typical symptoms as well as frequent symptoms. But the recall is lower than 40%, even for frequent ones. On the other hand, the automatically extracted relations shows very good recall, but the precision is not as good as human curated ones. So as you can see, information extraction and text mining plays a key role in knowledge graph construction for healthcare. However, natural language could be very ambiguous. For example, one disease may have different names. Or one name, such as obesity, can point to different diseases, diagnoses, phenomena, or symptoms. So there are many existing annotated knowledge bases. You need to link to the text. You need to link the text to existing knowledge bases to leverage all of them for the inference. So the scale of the knowledge base are usually very large and cover many subdomains. So you may wonder, there are already many existing knowledge bases annotated by experts. Why should I do information extraction and build knowledge graph again? The first reason is that there is a lot of new information published and collected by EHR and PubMed. Medical doctors are overwhelmed by such information. Second, we need an efficient tool to process the knowledge, to reason over different types of concepts. Traditional tools such as logical inference may not be able to handle such large scale of heterogeneous sources and ambiguities. Moreover, there are many new kinds of knowledge corresponding even more than the representation of the first-order logic, such as the activities, states, events, and their relations. Therefore, we need to investigate what we can do with information extraction here. So for example, for the current COVID-19 pandemic, it's not possible to find existing knowledge bases. Most of the knowledge is shared in the literature of the research articles. So automatically extract information would help organization of what we have known so far and help doctors develop their knowledge and the strategy to deal with the disease. Here I show some existing COVID-19 related knowledge graphs. The first one is led by UIUC, and they have extracted tens of thousands nodes with hundreds of types. A distinctive feature of their knowledge graph is that they can access different modalities of data, such as figures in research papers. Another one was done by Berkeley Lab. They also extracted tens of thousands entities emphasizing on more drugs and genes. UT Austin's knowledge graph also has hundreds of thousands nodes. An interesting result shown in their paper is that they retrieved the related disease and drugs to the new drug, remdesivir. There are also some industrial efforts, and they built their even larger knowledge graph. Currently, the knowledge graph is only available through a demo. Next, I will introduce how we're going to construct such kind of knowledge graph from text and what can be done in the future to improve it. In general, information extraction can be categorized in different tasks. For entities and events. For entities, we need to excuse me. For entities, we need to extract the entity mentions in text and then categorize them or linking them to existing knowledge bases. For events, we also extract them to build their relations. Information extraction from text can be pattern-based or learning-based. Pattern-based approach usually use designed rules to extract information that reflects humans' knowledge about language. When there is less annotated data, pattern-based approach can perform better. It's especially good when considering OpenIE, where there is no predefined predicate or targeted relations in the knowledge base. On the other hand, when there is sufficient annotation, learning-based methods usually perform better as they have better generalization abilities to read more irregular text. Here I'm going to show you an example of patterns that can be used to extract useful knowledge. Some patterns are commonly used for general IE, but medical documents are usually written in written languages, and sometimes can be long sentences. So to improve recall, patterns may be extended. For example, in this sentence, in longs and in reds should be both aligned to previous subjects and predicate. Another issue is that after such pattern-based extraction, the predicates are not aligned. So usually a clustering-based method should be applied here to normalize the relations. Compared to pattern-based method, learning-based methods are now becoming more popular. Especially nowadays we have giant pre-trained models. This has also influenced biomedical data extraction. For example, in biomedical domain, many BERT-based language models have been trained, which are generally used to generate more, like some good contextualized word embeddings for text. Then the learning models will be applied based on the embeddings for downstream tasks. Here is one of the state-of-the-art BERT-based model, BioBERT. It's shown that it's very effective in many tasks. In general, the standard BERT-based model is fine-tuned over some biomedical related articles, such as PubMed abstract and full articles. Then different tasks are fine-tuned based on different kinds of supervision signals, like name entity recognition or relation extraction and so on. Now we start to introduce different information extraction tasks. We start from mention detection and entity typing, since these two tasks are highly related. To detect the mentions, we treat it as a word token classification problem. A typical label encoding mechanism is to decide the mention boundary by the beginning and the inset part. Then all other tokens are considered as outside. For example, in this sentence, we only need to label B disease and I disease labels to detect the right mention of that type. There have been many loss functions developed for such sequential tagging problems, such as using conditional random field. The mechanism can also be easily reduced to purely working on mention detection, where we simply set the labels to be B, I, and O's. In this case, we may have more training examples for each label, but if we want to do typing later, we need to build another model to get the classes of the entity types. Sometimes entity linking can improve entity typing, especially for fine-grained entity typing. The task of entity typing is usually trained based on distant supervision, where the annotation are weak signals, which could be simply anchor links in Wikipedia. So in this case, besides the weak supervision, when an entity can be linked to Wikipedia page, the categories of that page can also help to decide which type of the entity should be classified. Here is an example of the labeled results. The typing task has 72 entity types, including common biomedical types, as well as some COVID-19 specific types, such as coronavirus and immune responses. The results have been included in the UIUC knowledge graph. Different from typing, which tries to decide the category of an entity, entity linking tries to link the mention to an existing knowledge base. Entity linking can also be done with a two-step approach, where mention detection can be firstly performed, and then we do entity disaggregation. So the loss of entity disaggregation is usually a ranking loss related to a set of candidate knowledge base entities. Again, entity typing can also be used to help entity linking. Here is an example where only 24 supertypes are considered for entity typing. Then the typing will be incorporated into the linking results to remove some irrelevant types. In general, mention detection, entity typing, and entity linking are three related tasks. They have different annotation and loss functions to train, but they can help each other. For example, when typing is more difficult, where there is very few annotation or the number of tabs are large, then adding linking results as features could be helpful. While linking is more difficult, for example, when there are more out-of-sample entities in the test set, adding typing features would be useful. In the literature of general NLP, there are already some existing works doing linking and typing jointly to improve each other. So given the entities, we also want to know what are the relations between each other. And this is what relation extraction does. The task of relation extraction in biomedical domain can have different subtasks. For example, to extract the relations between drugs and disease, drug and genes, or diseases and genes. A more concrete example is shown in the bottom. In this sentence, the entities should be identified with a tab, which is the task of entity typing. And then the relations are determined by the expression of words in the sentence to classify the pairs of the entities into a predefined relation category. Machine learning can be applied here for relation extraction. It is important to know the dependency between the related entities. So a dependency parse tree is widely used in building the initial relations. However, sometimes the the best dependency parse tree might not be able to capture all possible relations between words. So a recent work proposed to use several top best trees and get as many relations as possible first, and then used a graph neural network to automatically learn which relation could be more useful to determine the final relation between two entities. Another typical relation extraction in biomedical domain is for n-array relations. This is very useful because in biomedical literature, the facts are usually involving more than two arguments. For example, the use of a drug needs the information of the disease, the dosage, and the form of the dosage, and the target group. Only extracting the drug and the disease may only observe partial information. Partial information may be very useful for common sense knowledge, but for biomedical domain, it's obvious that we prefer to have more accurate information. A graph-based LSTM can also be applied here to extract n-array relations. As there's no trigger argument definition for n-array relations, a graph-based representation learning is more appropriate to aggregate all related information to make a decision. A multi-class classifier can be applied here to identify typed entities. And then the relation classifier will make use of the features extracted by the graph LSTM to make final decision whether we extract a set of entities to satisfy a particular relation. There is another type of information extraction called event extraction. Different from entities and relations, event is more complicated than them. And sometimes relations can be used to determine the inner relations between event arguments. Similar to event relation extraction, there are many subtasks for events. According to BioNLP in 2013, there are several domain-dependent tasks. They all share similar annotation schemes. For example, they need to annotate the span of the entity or the event trigger. Then they need to determine the type of the event and the relations between trigger and entities, and etc. So here is a comparison of the entity, relation, and events. Entity extraction is the simplest. Relation extraction determines the binary or n-array relations among entities. For events, we first need to identify the triggers. Here, effects and growth are triggers. And then we identify the relations between the entities, such as the cancer here and the activity growth, or the chemical compound L name, which is the cause of the activity effect. It's also to think about using a two-step approach to extract events. The first step is trigger identification and classification. And the second step is to do argument identification and argument role labeling. So both of the steps can be done with a learning-based approach. For example, in this example, a tree-based LSTM is used to get the representations based on the dependence parse tree. Finally, we also want to identify the relations among events. Event relations are usually in the form of temporal relation extraction, narrative schema, or discourse analysis in NLP. A recent work has been proposed to analyze the biological processes with more domain-specific relations, such as cause, enable, prevent, and super. In general, they also need to first identify the triggers and arguments, and then identify the relations between events. So the relations between events can be used to answer questions that are related to biological processes. Basically, they need to parse both reference articles and the questions into the same structure. This is the parse of the article, and this is the parse of the question. And then they match the patterns to find the answer node in the reference knowledge graph extracted from the article. So obviously, the data of such process understanding is still very small. There is much work to do for events and their relations in the future. So okay, we have introduced how we can extract useful information to construct our knowledge graph. In fact, by knowing that we have many ways to do information extraction, we realize that our knowledge graph can be organized in different forms. Therefore, we also need different representation tools to represent the knowledge graph so that many more machine learning algorithms can be applied. So next, we will firstly briefly introduce the possible representations, and then finally show some typical QA examples as knowledge graph applications. A knowledge graph is quite different from other types of graphs, such as social networks. A knowledge graph is typically a semantic network or an information network with semantic meanings. So therefore, the entity's instance can be categorized, and the type of the concepts are usually organized as a hierarchical trees. Therefore, when representing the knowledge graphs, we need to consider the structural and typed information. We can use a multi-relational graph to represent the knowledge graph. A multi-relational graph usually distinguishes the relations between edges. Therefore, modeling with such graph requires special treatment of the typed relations. For example, a typical multi-relational embedding method trans-D treats the triplets in the knowledge graph as translational functions, where the head entity embedding plus the relation embedding needs to be similar to the tail entity embedding. In this way, different types of relations can have different representations to connect entities. This is currently one of the most popular way of doing knowledge graph embedding. The loss is then to maximize the difference between a valid triplets in the knowledge graph and the sampled one. There have been many extensions to this method, mostly modifying the scoring function. For example, the recent model rotate can characterize all four properties, including symmetry, antisymmetry, inversion, and composition relations. Another representation is to treat a knowledge graph as a heterogeneous information network. Different from multi-relational graphs, a heterogeneous information network also treats entities differently with different types. When only considering node embedding, heterogeneous information networks may not have much advantage compared to a multi-relational graph. However, when considering higher order relations, it's much useful. Here I show a metapath semantically meaningful to compute the similarity between disease and symptom. The similarity is bridged by patient. So all similarities can be simply computed by matrix multiplication. We have a disease patient matrix, and we have a patient symptom matrix. And then the disease symptom matrix can be simply done by the multiplication of the two matrices. So similar to this disease patient's metapath, similar to this disease patient symptom metapath, we can also define many metapaths or metagraphs over the original heterogeneous information network. So given a metapath, it's also natural to extend the existing homogeneous graph embedding method. A typical method is based on random walk. Here is a random walk guided by the metapath, which is semantically meaningful. Then the embedding that can be learned by standard skip-gram algorithm will eventually reflect such kind of human knowledge. Another representation of a knowledge graph is called attributed network. In fact, we can obtain a lot of attributes from existing knowledge bases, such as Wikipedia, where the info box show a lot of attributes values. Moreover, recently, it's becoming interesting to use information extraction to extract some attributes from the text. So given the attributes, we naturally need to use a different learning algorithm to get the node embeddings. It's already found that we can separate the attribute relations from other types of relations in knowledge graph embeddings. Then the attributes can be incorporated into the node embedding in another signal channel. In this way, the node representation can reflect the two types of information. The first one is the attribute value, where nodes have similar attributes should be similar. The second one is the topological structure of the graph, where nodes with similar neighborhood should be similar. It seems that although some researchers have already pointed out that it is very important for this kind of representation, it's still under consideration for the biomedical or healthcare community. As we mentioned, a knowledge graph can also be a tree, especially the hierarchical definitions of the medical or biological concepts. Therefore, it's also natural to consider tree-based representation learning method. In general, we can develop different types of embeddings based on different geometrical observations, including Gaussian embedding, box embedding, and hyperbolic embedding. For example, in hyperbolic embedding, the hyperbolic space is naturally reflecting the tree structure. The Polytechnic model defined over the projection of the hyperbolic space can, this is a projection, show very natural tree-based relations. In fact, in the Polytechnic, the distance between 2 points that are near to the central are actually small, while the distance between 2 points that are near to the boundary of the Polytechnic is very large. So this is very different from the perception of the visualization of the Polytechnic. But anyway, the representation of the tree node learned by the hyperbolic space is quite efficient. Usually, it needs less dimensions to represent nodes of similar quality compared to other embedding methods. Finally, I would like to mention some applications of the knowledge graphs that can be solved by recent developed graph-based learning method. The first one is a knowledge graph question answering problem from this nice work at NeurIPS 2019. A typical question is, what drugs are likely to target proteins involved with both diseases X and Y? Instead of using traditional semantic parsing or mapping solutions, a natural way to consider is to use a neural network method. This neural-based method can directly model the questions as a set of semantic operations. In this example, two target proteins needs an interaction operation in the database query. Then they apply such kind of QA problem to a reasonably large knowledge graph containing drugs, diseases, proteins, side effects, and processes. So in general, the intersection operations can be done in the continuous geometric space instead of a symbolic inference. In this example, firstly, they identify two diseases, and then they attend two proteins, and then they need to perform an intersection operation over these two proteins, and then to compare with the result. So then it becomes a similarity measure problem between the intersection results and the target answer. After representing the QA in such a way, we can actually design a corresponding loss and learn it from huge amount of data. Results show that such kind of subgraph matching can solve several kinds of semantic subgraph searching problem. Another prediction problem is that rather than answering the what problem, we can also answer how many questions using neural models. For example, we want to know how many drugs are likely to target proteins involved with two diseases in the knowledge graph. In this way, we need to represent the knowledge graph as a heterogeneous information network and count the subgraph isomorphism in the knowledge graph. In particular, we can borrow the idea from NLP to treat such a problem as a QE problem, where we represent both query graphs and data graphs in the geometric space. Then the counting problem can be predicted by using final representation after interaction between the query and the target representations. Specifically, we can borrow the idea of memory networks to iteratively memorize the interaction between the query and the target graph. So if you would like to know more about the details of this work, please attend to our work at this KDD. So to conclude, in this part of the tutorial, we covered the topic of knowledge graph construction and inference in the healthcare domain. It is a very promising and fastly developing domain. Many recent works have been published. There are also many possible directions using knowledge graphs, such as personalized dialogue systems or recommender systems. With that, I can take questions. Thank you.
Hi, before we move to the next chapter, if you guys have any questions, feel free to type in or ask us, and we are very happy to take any questions. So we will move to the next chapter.
Hello everyone, this is a KDD 2020 tutorial, Recent Advances on Graph Analytics and its applications in healthcare. Thanks for your coming. This is Chen Xizang from Weill Cornell Medicine, Cornell University. Please refer to this webpage for the tutorial materials and outlines. In this tutorial chapter, we will focus on graph generative models and drug discovery. This tutorial is based on our latest work on AI-driven drug discovery, MoFlow, and invertible flow model for generating molecular graphs. This is a joint work with Professor Fei Wang from Weill Cornell Medicine, Cornell University. Drug discovery and development consists of following cascading steps based on the discover the target protein of a focus disease, then to screen millions of functional molecules to inform design. This step is called lead discovery. The next step is lead optimization, which means to design, make, and test more than 1,000 of new molecules with optimized property, and then followed by preclinical experiments and then human clinical trials, including 1, 2, 3 phases. Overall, going through such a path is very lengthy, costly, and always ending up with a failure. Specifically, the average cost of developing a successful drug is estimated to be $2.6 billion. And it takes at least 10 years to translate it into patients with only 12% success rate. Here, our works focus on lead discovery and lead optimization, namely drug discovery process in short, which takes approximately 5 years and accounts for 1/3 of the total cost. A critical question to be answered is how to accelerate the process to reduce its cost and to increase success rate. Even the first step, lead discovery, is very challenging. The chemical space is very big, but largely unexplored. The scale of drug-like small molecules is up to 10 to 60. However, existing chemical database is at the scale of 10 to 6. We can see such a huge gap between them. We cannot exhaustively enumerate all the 10 to 60 molecules. How to efficiently explore such a big chemical space is very difficult. Lead optimization, which tries to optimize molecules, is also very difficult. To design novel molecules with optimized properties needs to high throughput screen existing database or based on medicinal chemist knowledge. To evaluate the candidate molecules needs very expensive in vivo experiments or expensive in silico simulation. How to efficiently optimize molecules guided by the targeted properties is very challenging. Our vision is drug discovery driven by AI and big chemical data, with ultimate goal to reduce time, cost, and failure rate of drug discovery processes, maybe from 5 years to 5 months, to efficiently explore 10 to 60 scale drug-like chemical space, and to efficiently and automatically design novel molecules with optimized properties, leveraging both knowledges learned from big chemical data and medicinal chemists. Specifically, we define our problem as follows. Our goal is to generate novel molecular graphs with optimized properties. Our data are discrete two-dimensional molecular graphs. For example, metformin on the right and its two-dimensional graph representation. We have multiple molecular graph samples and their corresponding properties. Our outputs are novel molecular graphs with optimized properties. Why is this problem very hard? First, we are faced with discrete molecular graphs, data, and their combinatorial complexity. Here, nodes represent atoms, and for example, carbon atom, hydrogen, oxygen atom, and so on and so forth, and edges are bonds. For example, single, double, and triple bonds in physics. Both nodes and edges have multiple types. The combinatorial complexity of the small molecule graphs space is near 10 to 60. Besides, existing deep models are majorly designed for regular grid structures instead of graphs with multiple edges and multiple types of nodes. Second, why is it very hard? Molecular graph optimization task is novel and very complex task, which consists of 3 subtasks, including graph generation, graph property prediction, and graph optimization. Graph generation means to learn a generative models, namely a distribution of graphs. Generation is just the sampling from the learned graph distribution, PG. Graph property prediction means to learn a mapping, FG, from discrete graph space to continuous property space. Graph optimization means to design new graphs, G prime, with optimized property. Thus, we need efficiently search discrete molecular graph space and sampling novel molecular graphs from this space. Guided, pay attention to guided by the property functions, which is a mapping between graph space and its property space. Third, why it's hard? Encoding graph is hard. Decoding graph is much harder. As discussed in the previous tutorial, we need to encode, or to embed, or to inference with graph inputs. To design molecules with a combinatorial structure is a reverse process, namely to decode or to generate graph outputs with multiple types of nodes and edges. What's more, the generated graphs are not trivial graphs. they must follow balancing constraints in nature to guarantee chemically valid molecular graph structures. And we also want to generate novel graphs as many as possible. Here we will introduce some related works on how to generate molecular graphs. One of the seminal work is graph VAE model, based on the variational autoencoder framework. The authors try to generate small string representations of graphs. Here we can see the molecular graphs and its one-dimensional string representations. Their limitations are sequence loss a lot of structure information of molecules, and thus they show very limited performance. Junction tree VAE models tries to incorporate graph structures into VAE models. On the top right, we can see structure information of molecules is better kept by graphs. Two very similar molecules have quite different strings representations. And the junction tree VAE generates chemically valid molecules by capturing valence constraints on graph. However, GTVAE can only handle tree structure moleculars, and the generation of molecular need very expensive sampling in the latent space. GAN-based model MoGAN is also proposed for molecular graph generation. However, MoGAN cannot guarantee chemically validity of generated molecules, and GAN tend to have mode collapse problem. In this scenario, mode collapse means to generate a lot of duplicated molecules, which means they generate very few novel ones. The state-of-the-art results are achieved by autoregressive based models, for example, GCP and OpGraph AF. They generate a molecular graph in a sequential manner. At each step, they generate an atom or a bond and then check the validity of the current graph. If the current graph violates the chemical constraints, the generation process terminates by reject sampling. However, the sequential generation is very expensive, and they tend to generate very long and strange graphs as highlighted. Graph NAP tries to generate molecular graphs by normalizing flow generative frameworks. However, they only use single add coupling layers in the normalizing flow structures. We will detail this part later. And its neural network structure is unstable to train, and their model can only generate very few chemically valid and novel molecular graphs. Thus, they show very limited performance. We summarize related works by their data. For example, sequence representations and graph representations, and their generative frameworks, including autoregressive model, variational autoencoder model, generative adversarial networks, and normalizing flow models, and their optimization method. For example, for VAE models and flow models, they tend to use gradient ascent method searching the latent space. However, for autoregressive models, they tend to use reinforcement learning to optimize molecular properties. Here, we focus on molecular graphs, normalizing flows, and naturally to optimize molecules by gradient ascent in the latent space. We will first introduce basics of normalizing flows and show why we choose normalizing flows as our basic generative frameworks. In this tutorial, we covered the basics of normalizing flow framework. Normalizing flow is an invertible generative model. We try to learn an invertible mapping F theta, which maps complex original space to latent space, which is a simpler space, say Gaussian. The generation process is a map from latent space to the original space by invertible mapping. We can learn the modeling parameters by exact maximum likelihood training. Each layer of the deep network structures must be an invertible layer, and the computational of the Jacobian determine this part should be efficient. There are two constraints of such neural network structures. Here, we will first show one of the most basic structures, nice models. Nice models try to build invertible layers by splitting dimensions and use residual flow updated alternatively. For example, this is the input signals. They split into two parts, x1 and x2. They keep the x1 the same and use x1 after transformation to update x2. And then here is the output of the latent space. They use x1 to save information for reversing and use x1 and this residual part to update x2. Thus, the reversing mapping is just as follows. How can we build deep models? So we can stack these layers layer by layer by alternating update different parts. For example, this layer, we keep x1 the same. For the next layer, we keep x2 the same, z2 the same. Another update updates of the nice model is real MVP models. They follow the same idea, splitting dimensions and to build invertible layers. However, they introduce affine transformations. So instead of just the residual part, they multiply this by an exponential scale to make it more powerful. And the reverse mapping is just as follows. Similar ideas to build deep invertible neural networks by alternatively update different parts. Later, the state-of-the-art performance is in the CV community is achieved by GLOW model. GLOW models introduce another two layers to make it more powerful. The first one is ActNorm, which is a normalizing layer to make the learning dynamics more stable, and which is also an invertible transformation. Another is an invertible 1x1 convolution, just like the graph convolution, but it is 1x1 convolution. So such a convolution layers makes the transformation more powerful and makes it can enhance the express powers. And also they follow the affine layers to build the invertible transformations like this. Why flow frameworks? We just summarize the state-of-the-art flow frameworks, but why we choose such an invertible mapping generative models? Because its invertible mappings enables generating more novel molecules. For example, VAE, GAN, and autoregressive models are not invertible as shown in these diagrams. They can only reproduce, this is the training data, they can only reproduce part of the training data, and they can also generate some different extent of novel molecules. In contrast, flow models can reproduce all the training data by invertible mapping and generate more novel molecules, which means flow learns a strict superset of training data space and explores chemical space further and better. Besides, normalizing flow frameworks have following merits. They have exact maximum likelihood training. Compared with VAE and GAN, they are not. Efficient one-shot inference and generation, while autoregressive models generating molecules step by step, but our model can capture molecular graphs in a holistic way. Also, we will show the better performance later in the experimental chapter. So here is the idea of our model flow to generate molecular graphs. A molecular graph consists of atoms. and the bonds. Atoms are nodes with multiple types, for example, carbon, nitrogen, and oxygen, so on and so forth. So we can encode atom as a one-hot atom matrix. Bonds are edges with multiple types, for example, single, double, and triple edges. We encode bonds as a multi-channel tensor similar to image. In order to capture the discrete atom bond structures of molecular graphs, we decompose the probability of a molecular graph into two parts: the probability of bonds and the conditional probability of atoms given bonds. We can use any flow models to generate and to model to learn bonds probability PB, which generates the graph skeleton of molecular graphs. Given bonds, we propose a novel graph conditional flow FA given B to generate atoms given bond skeleton. Then we assemble bond atoms and bonds into a chemically validated molecular graph. We illustrate our model as follows. We use a globe-based model to model bonds probability PB, which encodes multi-channel edge tensor into latent space. Given bonds, we propose a novel graph conditional flow FA given B to encode atom matrix given bond tensors. We encode the discrete molecular graphs into continuous latent space, modeled by simple Gaussian distribution. We can sample from latent space and use inverse mapping to generate bonds tensors and atom matrix, respectively. And then we assemble atoms and bonds into a chemically valid molecular graph. Here are some details. We use a variant of globe for bond generation. Here we transform edge tensors by a variant of globe framework. First, we squeeze edge tensors to make it have more channels, just like this. And then use the same active norm layers to make the signal normalized and make sure the deep structures are stable. We also use invertible one-type-1 convolution to transform the edge signals, and use the split and affine transformations to build and update the edge signals and keep them invertible. Here, we use sigmoid instead of exponential to make the affine transformation more stable. And we use 3x3 convolution, batch norm, and ReLU to transform B1 and to update B2. We can use arbitrary graph neural network structures here. We can build deep structures by alternating updating. Here is just a one layer of invertible layer. As we discussed, we can use any flow to learn bond tensors probability PB, which generates a graph skeleton. However, to generate atoms is not trivial. Given bonds, we propose a novel graph conditional flow for atoms given bonds. Skeleton. Here we use both atom matrix and bond tensor as inputs. First, we also use active norm two-dimensional to normalize atom matrix, and then follow split techniques to build invertible structure. For each layer, we only update each atom and each row by the remaining atoms, and their link structures. We use the remaining atoms and their linked structures by a multi-channel graph convolution. We convolute each channel of the tensors and then sum their signals. Here we use multi-channel graph convolution, batch norm, ReLU layers, and a multi-layer perception to summarize their information. Here we also use affine fine coupling structures to make it an invertible transformation. Also, we use sigmoid here. We can build a deep invertible neural network by alternating update in the next layer. All right, here are after some math details. Again, let me show the overall structures, frameworks of our model. Our model flow can embed or inference or encode discrete graph structures into continuous latent space. And the generation is just a sampling from this latent space and use its reverse transformation to generate the molecular graphs. We can also use another multi-layer perception, which mapping from latent space to property space to do molecular graph property prediction tasks. So here is a full regression. Thus, guided by the gradients of the properties, these regression parts, property prediction parts, we can search the continuous latent space of a molecular graph and then generate optimized molecular graphs. We check the valence constraints by this equation. The number of bonds linked to one atom I should be smaller or equal to the valence of these atoms plus its formal charge. For example, a carbon atom can have 4 bonds. An oxygen atom usually have 2 bonds and up to 3 bonds when it has extra charge. We modify the generated molecular graphs into a valid one by this validity correction process. If the current molecular graph follows valence constraint, we return its greatest connected component. Else, we delete unnecessary bond or add additional charge to the invalid atoms according to chemical rules. We validate our models by 4 tasks, namely molecular graph generation and reconstruction, visualization of continuous latent space of graphs, molecular graph property optimization, and constraint property optimization. We'll elaborate each one in detail. The first experiment is molecular graph generation and reconstruction. The problem is as follows. Inputs are molecular graphs. Our models try to learn a generative models, i.e. the probability distribution of graphs and its invertible mapping F. Generation is just sampling from the latent space and use the invertible mapping to generate discrete graphs. Reconstruction is try to reconstruct the molecular graph from its latent representations. Our goal is to generate valid, unique, and novel molecular graphs. Here we use 2 famous molecular graph database. One is QM9, it's a relatively small database with at most 9 nodes. And Zinc is a much larger one with at most 38 nodes. How to evaluate our generation performance? We use following performance evaluation metrics. Validity, which means how many chemically valid molecules are generated by our models. Validity without correction or check, because some models use post hoc corrections and our models use corrections to ensemble them. If our method don't use them, what are the validity performance? Uniqueness measures the percentage of the chemically valid and unique molecules in all the generated molecules. Because some models always generate duplicated molecules. Novelty is a very important one, which means to generate a novel molecule which are not exist in the training database. Reconstruction rate means how many data set we can remember and reconstruct from their latent representations. Here, we can summarize above ones by NUV, which means the percentage of novel, both novel, unique, and valid molecules in all the generated molecules. Here is a matrix we propose a comprehensive matrix to evaluate the different models. Here our models compare all the state-of-the-art methods. For example, all the flow-based models, graph MAP, graph GRF, and graph AF. Our models guarantees 100% validity. If without corrections, our models also achieve the best validity. Our models can generate diverse and unique moleculars, and also achieves the top novelties. Thus, our model achieves we can generate more novel, unique, and valid moleculars. Because our models are invertible, which guarantees 100% reconstructions. Here we also compare the VAE models, autoregressive models, and the flow models. Our models can achieve 100% reconstructions, can generate more novel, unique, and valid moleculars, and 100% valid moleculars. And if without correction, our model also achieves the best performance in validity compared to the state-of-the-art results. Thus, our model flow explores the big chemical space further and better. Here we visualize the latent space of our model. Our model can encode and decode between discrete graph space and continuous latent space. For example, here we create interpolation around the latent representations of one molecular graphs and decode its neighbors. Here we visualize the decoded molecular graphs. We can see the latent space is very smooth by checking their graphs. Their graphs just change a little bit. We measure the graphs, the similarity between different graphs to the center graph by the Multimodal similarity. We can see the graphs change gradually in this two-dimensional latent space. We further do a very famous experiment, just as in the CV, a linear interpolation of phases. Here we do a linear interpolation between two molecular graphs. Here is the one molecular graph, here is another. We can see if we sampling from their latent space, the linear latent space, we can see a very smooth changing trajectories from one graph to another graph. We can see their similarities become their dissimilarities become larger and larger. The third experiment is property optimization, which means to generate novel moleculars with the best quantitative estimate of drug likeness scores, QED scores, as many as possible. We search the latent space by gradient ascent and try to generate the best and report the best molecular with the top QED scores. We can see the best performance by the VAE scores, autoregressive plus reinforcement learning methods. They can only generate two molecular with the best 0.948 molecular graphs. However, we can see our model flow generates more novel moleculars with the top QED scores. Here are top QED scores. We rank the top generated novel moleculars. Our models can generate much more than the state-of-the-art results. Here we just show some the performance, visualize some molecular graphs. All these molecular graphs are with the best QED scores. The fourth experiment is constrained property optimization, which means to find a new molecular graph G' from a seed molecular graph G. To maximize the similarity and the property is kind of multi-object optimization. Here we use Multimodal similarity of Morgan's fingerprint to measure the molecular graph similarities. For target properties, we use a comprehensive one named penalized log P, which is the octanol water partition coefficient log P, penalized by the synthetic accessibility as a score and the number of long circles. Here are the results. We compare our models with the state-of-the-art methods, GTVAE, GCPN, and GraphAF. Our model achieves the best similarity and the second best improvement. However, compared with the best improvement, our models can generate more realistic ones because the best performance are achieved by this particular long chains. However, we can see our models can optimize molecules by in a very subtle way. We can see this part. So this molecular show very worse scores, but our optimization method just change it a little bit, and we keep the best similarities and improve these molecules to a very large extent. Here we also randomly sample some molecular from the zinc datasets and optimize them. Here we can see our methods optimize the P log P by a very large margin from this large circle to these ones, and these ones to these circle ones to these ones with much better properties scores. So in summary, we propose a novel Malflow model for molecular graph generation, which consists of a variant of globe for bonds, a novel graph conditional for atoms given bonds, and which has a novel validity corrections to ensemble them. Our model is an invertible model with a fast inference and generation at one shot. Our model also achieves the state-of-the-art results. That's the results for generation and reconstruction with respect to novelty, uniqueness, validity, and reconstruction rate. That's the results for QED property optimization. We can generate more drug-like moleculars. Best similarity scores for constraint optimization, and the second best improvement scores for P log P. Please kindly refer to our paper Malflow and invertible flow models for generating molecular graphs for more details. And more information can be also found in my web page. Thank you so much. So let's give time to the next section, discussion part, and I'm very happy to take any questions later. Thank you so much.
All right, so we just finished this part, so I'm very happy to take any questions. And also we will move to the next part.
Hello, everyone.
By Professor Fei Wang.
Welcome to the last part of the KDD 2020 tutorial on recent advances in graph analytics and its applications in healthcare. And my name is Fei Wang. I'm currently an associate professor of health informatics in Department of Population Health Sciences at Weill Cornell Medicine. And we have already heard a lot of the technical advances on this direction in the previous parts. And I am going to do a brief summary and discuss about the future directions, including challenges and pitfalls on this direction. So I wrote a perspective that was published on JAMA Internal Medicine in late 2018, and where I discussed a lot of the points for us as the data mining researchers. So when we develop algorithm for analyzing healthcare data with the goal of helping healthcare, so what are the important points we need to pay attention? Although I put deep learning in the title, but a lot of the items are generally applicable to other type of algorithms as well. So the first thing we have to keep in mind is the data quantity. So different than other application scenarios like the, the images or the speech or the natural languages where the algorithms like machine learning, deep learning, AI type of algorithms have achieved a lot of success. So the sample size in medicine is usually not that huge, or it's a lot of the times impossible to get a huge amount of samples. In medicine, for example, a lot of times we do individualized prediction, where every sample is essentially a patient, but all over the world you just have 7 billion people, and it is impossible for you to get the data from all of the people all over the world. And what's more, the complexity of the diseases is usually much more complicated than like image recognition or speech recognition. So this makes it a lot of the times the medical data analysis problem small, what we so-called the small sample problem. So in order to solve that, so one important thing is to see if we can get as large sample size as possible, because the patient population are distributed in different hospitals, in different states, in different countries. So, I mean, there are lots of course, privacy concerns. I mean, a lot of the healthcare information are sensitive. So how can we effectively leverage the information from different places without leaking the privacy? So that's one important direction to consider on this. So the first step, if you want to integrate the data, you have to define a unified standard. Like, for example, we work a lot on electronic health records, but I mean, different hospitals use different electronic health record system, and different systems use different codings for the diagnosis, for the medications, for the procedures. In order to let them talk without any problem, you have to let them speak the same language. So that's what we mean by a standardization. So we need to have a unified vocabulary, which we usually call data model, to standardize and harmonize the data from different places. There are lots of national and international initiatives or consortiums for this goal. Like this is a representative example called ODYSSEY, stands for Observational Health Data Science and Informatics. And the common data model they define is called Observational Medical Outcomes Partnership, or OMOP data model. So they map, doesn't matter what local EHR system you're using, but first, if you want to use the technologies or the software tools provided by ODYSSEY, you have to first map your local EHR data dictionary to this OMOP model, and then you can run whatever the software tools they provided. And this actually, ODYSSEY is an international initiative, and there are many countries that already joined the party, and which, I mean, all those hospitals in ODYSSEY, they're all over the world, including Europe, including like Asia Pacific, and also North America, and so on and so forth. And this standardization makes large-scale analysis possible, and this is one of their representative work where they analyze the treatment pathways for common chronic conditions, including diabetes and hypertension in different countries, and they collect data from different places, map them into the OMOP model, and use a unified statistical method to analyze the treatment pathways, and they find out some distinctions for the treatments for those different common chronic conditions.
But the way ALSI do for this large-scale analysis is they never let the local data go out. So basically, you do your mapping locally and you download the software locally, you do the analysis locally, you just report ALSI your summary statistics or the analytical results. And then on the ALSI side, so they're going to have some working groups or consortiums to do some meta-analysis on the results you reported. So the good way about this is you preserved the privacy pretty well, but the limitation is you don't really leverage the data across different places. You just do analysis locally and report the result, but you don't really leverage the data across local institutions. So one promising strategy to solve this problem is what is the so-called the federated learning strategy, which is basically you, what is shown in this figure is you have a central server and you also train your model locally. Of course, this also needs standardization first so that across different local institutions, they at least know who, what each other are talking about. And then let's say you want to train a model by leveraging all the data from different places, but you don't want any privacy information to leak. So basically the model got trained locally and the model parameters got communicated to the central server. And every time when there's a new data from local sites, the model parameter got updated, and you only communicate or transmit the updates of the model parameters to the central server, and after the model parameter updates are aggregated in the central server, and it got dispatched back to the local places. So and you further update the model parameters locally, and you do this in an iterative fashion. So the good thing about this federated learning strategy is you preserve the privacy because the data didn't go out as well, but at the same time you got the model parameters updated in a centralized way. So in that sense, you basically kind of like leverage the information which is reflected in the updated parameters of the model at different local institutions. So this is a more like you can basically achieve more compared to you just to analyze the results, via meta-analysis, like in the previous ALSI example. But here, in the federated learning strategy, you still face the risk. For example, is there any potential risk that you transmitted your model parameters to a central server? Is there any risk for the central server to be attacked? So there are lots of research in recent years on federated learning on how to further protect the model parameters by injecting the different privacy strategy, let's say, or let's just get rid of the central server and let the entire system work in a decentralized way, such that the local institutions only talk to their neighbors, and so on and so forth. So this is a very promising strategy for federated learning to work in a healthcare setting. And another thing is the transfer learning strategy. So this is an example on training a deep learning model for analyzing medical images. A lot of the times it will be super challenging for a local institution to have tens of millions of medical images to train a monster deep learning model from scratch. So a common strategy is you have the model trained on a huge available image data set like ImageNet. Although it is a natural image, but they still share a lot of common characteristics as images with the medical images. And then you just change the final classification layer, and you can. There are several different versions of this transfer learning strategy. You can either fix all the previous layers for feature extraction, but just retrain the final classification layer, or you can use parameters on the previous feature classification layer as the warm start to basically use your local medical image to fine-tune the model parameters. So this is kind of like we transferred knowledge learned from the natural images to the medical image. And also we have a paper last year on KDD to investigate the possibility of leveraging meta-learning to transfer the knowledge from let's say we want to disease onset prediction, early prediction of disease onset, and let's say our target disease is, has small sample size, and how can we leverage similar disease conditions which may have a bigger sample size to train the model, and the knowledge of learning the model can be transferred to the learning of the risk predictor of the target disease. And we do this via the meta-learning strategy, where we use this MAMO, a model agnostic meta-learning strategy, and we get a good performance. And so we talked about to handle the data limitation or the small sample size problem. We need to do in order to leverage all the different data set, you have to standardize the data, let them talk with the same language first, and then you can do federated learning without touching, leaking the privacy. And you may also want to leverage knowledge transfer from similar tasks. And the other thing is we have introduced the knowledge graph. So how can we leverage, because biomedicine is a field where we have a lot of really important biomedical knowledges from historical, let's say, biological experiments or clinical trials or clinical management, so on and so forth. These knowledge are super important to guide the learning process towards the right direction. So how can we leverage those biomedical knowledge extracted from the biomedical literatures and integrate that into the data, let's say a healthcare data mining process. This is just one example on integrating the knowledge graph with the local EHR data analysis. And the paper was conducted by the UCSF researchers and published on Nature Communication. So these are, how to handle the small sample problem in medicine will be a very promising direction and very important. And then the second thing is data quality. So we not only have small sample size, but a lot of the times there are a lot of noises, especially in clinical data. So we talk about how to analyze data, but can we also design algorithm to improve the data quality? Also, another important direction to consider. So one example is the IBM Watson Imaging Clinical Review, where they compare the information from the EHRs and the radiology or pathology reports and find the discrepancies, where could be the places that there could be some errors or noises, and you can highlight to the clinicians or nurses who input the information to basically alert them, and so that the data input data quality could be improved. And this is another problem, like we use the clinical notes in the electronic health records to predict what could be the correct diagnosis code or procedure code. So if there is any discrepancies between the codes and the codes you predicted, then there might be some problem or some noise or error. So these kind of problem is also very important, because data quality is crucial for us to design good algorithms. Otherwise, we're going to suffer from the so-called garbage in, garbage out problem. And model interpretation, I think we have heard this a lot. especially in medicine. So we can think of if you give some risk predictors or some treatment suggestions without giving the exact reason behind that, it is unlikely, or it would be very difficult to to convince the clinicians to adopt the model. So by default, we think model interpretation would be very important. And of course, we hear a lot of debates on this topic in recent years. Like Hinton said, I mean, for a lot of the problem, human cannot even explain how they work. I mean, a lot of the problems for our brain is largely unknown. So our brain is essentially a black box model. So why do you expect to know everything? And of course, there are some opposite opinions saying that why we need explainable AI. And there are also some, I mean, this is Cynthia Rudin, who is our keynote speaker last year, talking about we have to design transparent model for high-stake decision scenarios, such as biomedicine. And actually, I wrote a piece earlier this year to Annals of Internal Medicine discussing this, because when we talk to the clinicians, actually there are some interesting opinions from them. What they say is, like, for a lot of the medicine, like aspirin, so which is widely used for tens of years, but the mechanism of how it works is still not crystal clear. But largely, I mean, the doctors know what this medicine can do, and it got widely validated. So basically, the doctor said, I mean, it's okay if the model is completely black box, but I mean, it is important to get it evaluated or validated in a lot of the critical places so that we understand the risks and the generalizability. So that's important. So this means that actually a lot of the times, the scenarios on why we need interpretable or explainable AI, even in biomedicine, it really depends on where your algorithm going to be deployed. So for certain scenarios, like in clinical decision support, it would be very important for the algorithm to be interpretable or explainable. But for some other places, like natural language processing or some pre-processing, or even sometimes image-based screening type of places where, I mean, the decision is not that high risk. I mean, if you can show, of course, I mean, how to evaluate that, most importantly, in a prospective setting is something very important to do. But as long as we understand its effect or how it works, and we understand the risk, then it is probably okay to basically have a high-performance black box medicine. Because if we emphasize, we don't want black box model too much, it may hinder the development of some chance, because in a lot of the places in biomedicine, like the predictive model, they still don't work very well. So if we say we only want a transparent model, then it may hinder the development of the potential of some high performance black box models. So we should make our mind open. And the third thing is this data bias, model generalizability issue. We have heard a lot of relevant discussions and papers in recent years. So this is an opinion from my colleague, Dhruv. He said, this AI could worsen health disparities because of the data it was trained from and its black box nature and so on and so forth. And this is another paper, actually viewpoint, discussing the potential disparity of machine learning models in dermatology. If you know that there is a Nature cover article about using convolutional neural nets, which is actually the Inception version 3 model, to classify the skin lesions as either melanoma or no. But this paper said, so you should be careful. So this is kind of like the process. So when your training sample are from the people with different skin color, the performance might be different. Like in this case, the training samples are largely from US, Europe, and Australia. So, for the majority of the training samples, they're from white people. So the performance of the model to working on, let's say, Asian or African American, it may not work very well. So you have to really realize the potential bias in your training data set and get the skin color as diverse as possible, which is a very a good point and direction for us to consider when we develop the models. And this is another science paper discussing, actually there is an algorithm used for determining the enrollment, actually the eligibility of the enrollment of a healthcare management problem, where they have an algorithm that calculate a score to determine if you are eligible or no. But in that algorithm, there is one potential variable that is used, which is income. And that income basically can bias the model when they make the decision. And this figure actually shows that in order to get people eligible for that healthcare management program, so the black people needs to be much sicker compared to the white people. So this is one example on a widely adopted algorithm for determining the eligibility of people into a program that generates highly unfair decisions. So when we design algorithm, we have to keep this in mind and examine the potential sources of bias and try to make the model as fair as possible. And also, we have model security. We talk a lot about data security in healthcare. We don't want sensitive information to leak, but imagine in the future if there are lots of computational models, data mining models got deployed in the healthcare or clinical workflows, what would happen if the model parameters got leaked? So we all know this adversarial attack. It can fool the model, and this is an example of adding noises and make the model think of the turtle as a rifle. And this is how we fool the model. Used in an autonomous driving system, which is mixed. If you paste those patches and the recognition system thinks this is not a stop sign but a speed limit sign, so it can drive through. So there is a science paper discussing the potential of adversarial attacks on medical machine learning, where if you have image recognition model to classify those fundus image or chest x-rays or dermoscopy, and you add some carefully designed noises, it can easily confuse the model and let them make opposite decisions. And we also, this is in KDD 2018, so we also show this is also possible for what if you just do a slight perturb on the patient EHRs, and it can confuse the predictive model trained on the EHRs as well. So one potential threat of this adversarial behavior is in medical fraud, basically insurance fraud. If let's say in the future, I mean, now the insurance companies, they basically review the submitted claims and approve or no. Let's say if we, I mean, because there are, I mean, because of the huge amount of the submitted claims, it is a lot of the times impossible for human to review it by eyeball. But frequently, the insurance company is going to use some machine learning models to classify if this is likely to be a fraud or no. But I mean, let's say if these models get more and more sophisticated, and if we figure out what is the model parameters and the working mechanism, then there might be a potential that we can slightly perturb the submitted claims and basically to change the model decision. For example, if initially the model think it would be a false claim or a fraud claim, but after we change it in a certain way, we can make it pass. So the science paper gives an example. Let's say if you have this a claim from the dermatology, and if you change that, you can reverse the model judgment on whether this is a certain disease or no. Or you can even do a multimodal attack where you change both the image and also the associated clinical notes to basically make them match and let the fraud pass the approval. So these are some potential threats of the model security issue we're gonna need to keep in mind in our future algorithm development. And in short, I think these are just some of the aspects. So although we are developing all different kinds of models in all different kinds of scenarios like predictive modeling, disease subtyping, biomedical knowledge extraction, and so on and so forth, we focus on the performance a lot. We want the model to work well, but at the same time, there are lots of important characteristics. I would not say unique, but important to biomedicine that we have to pay attention. And here I just pick several, including the data quantity, data quality, the model interpretability, the potential bias, and also the model security. With no doubt that the advancement of those AI and data mining techniques can make medicine better and better, but it is important to understand the context and the domain-specific knowledge of biomedicine, especially different diseases, so that we can really understand the need and develop the right algorithm to tackle the right problem. And I would like to conclude the whole tutorial with this paragraph from the book Deep Medicine from Eric Topol, who is a famous cardiologist, and he is super enthusiastic about artificial intelligence. So the greatest opportunity offered by AI is not reducing errors or workloads or even curing cancer. It is the opportunity to restore the precious and time-honored connection and to trust the human touch between patients and doctors. Thank you very much. And this is my email and Twitter handle. And now we're entering the question and answering session. So feel free to propose any questions.
Hi, thank you so much. Thank you all the speakers. Can everyone hear me? Hi, Fei. Maybe and Yang Qiu. So maybe you can unmute your phones so we can take any questions and go further discussion.
Yeah, I can hear you well. I think Kunpeng just asked one question. Maybe you can answer that first.
Oh, yes. At first, thanks all the speakers and thanks all the organizers. So we are moving to the next chapter, QA and further discussion. So we just summarize a part of the questions. For example, the first one, let me repeat the question. Can you please briefly summarize the situations where flow-based models are not good at? Very good point. So in my mind, there are 2 points. The first one is, if you want to build an invertible model, so normalizing flow-based model is invertible, so you have some constraints. Such a you must follow such constraints to guarantee an invertible layer. Thus, the modeling complexity is so it's a little complex to design and implement the invertible layer. And also you have some constraints, maybe limited is expressive power. But the benefits of invertible mappings is, I mean, there is no information compression or no information loss. It's a 1-to-1 mapping. So if we examine each point in the latent space, we can find a 1-to-1 mapping in the original data space. So maybe that's the reason why the flow-based models can generate more realistic and novel data. So it's difficult to, I mean, it's a totally black box. Just as the Professor Fei Wang has mentioned, it's a little difficult to understand what's going on in the invertible layers. So we can see this structure is very difficult. As a result, so follow these questions. So we try to propose some visualizing tools to understand complex normalizing flow-based frameworks. So we try to visualize their, I mean, their intermediate outputs and their final outputs. We try to visualize their generated graphs to help us better understand the normalizing flow frameworks, just like this. So this is also our following works. It's an ongoing work in the workshop paper. So in the tomorrow's workshop paper, visualizing deep graph generative model for drug discovery. So maybe you can refer to our ongoing works. So this is the answer to that question. So can I propose another question to Professor Fei Wang? I will direct this question to Professor Fei Wang. And because we just show many different parts of the graph mining analytics, for example, embedding, GNN, graph flow, knowledge graph, and so on and so forth. They are complicated and very powerful in the I mean, baseline scenario or well curated data set. But in the healthcare, just like in the pandemic, we are faced with a very strange and difficult scenarios. How to apply our existing method, complex methods to the emergent pandemic scenarios. Can you give us some perspectives on how to apply these techniques to the, say, the COVID-19 or the pandemic to help us to go back to normal?
That is a good question, and I think in this KDD there are quite a few COVID-19 related sessions or panels or keynote talks, and I noticed on Huba, I mean the app for KDD, there is actually a group called Data Science for COVID-19, and I think there are lots of great discussions there. And I think according to my own experience, I have done a lot of COVID-19 related research in recent several months. I think there are, if you look at the papers out so far, I mean, integrating data science and COVID, there are several major areas. Like the first one is epidemiology, like we want to predict the outbreak and like the medical resource allocation, like the need for ICU bed and so on and so forth, this kind of thing. Where conventionally they're mostly epidemiology models and which are based on very explicit assumptions on the dynamics of the entire, let's say, case increasing process, which may not fit in the actual real world data. So a lot of people trying to integrate the data-driven model with the epidemiology model to achieve more accurate performance. That's number one. Number two is about this developing mobile app to do contact tracing or to capture the patient-reported symptoms or outcomes to derive like the symptom subphenotypes of COVID-19 or to track the contact of the COVID positive patient, so on and so forth. This is, of course, one big area where the data science can be really helpful in terms of the controlling the pandemic. And the third thing would be like on basic science side, like the drug discovery. I think Chengxi just mentioned one example on developing algorithm to discover drugs in silico about the potential of design a novel chemical to treat the COVID-19, but it usually takes, billions of dollars and tens of years, which is a little bit, given the current urgency, a little bit a long-term or not really realistic to solve the current urgent need. So there are lots of works on drug repurposing. I think we heard from Peng's, network embedding and graph neural network session, as well as Yang Qiu's knowledge graph session. So how can we integrate the existing knowledge about those biological entities related to drugs to identify the potential drugs that are already on market that can be potentially retargeted to COVID? Actually, one example, one of the most successful drugs so far is the remdesivir, which initially was developed for treating Ebola, but it turns out to be an effective antiviral drug for treating COVID-19. So although its discovery is not based on big data, but it indeed shows the potential of drug repurposing because there are so many drugs and so many diseases. So discover their potential linkage, definitely a big data can help. And I think the last one is the clinical. So we have, my team has done some works on like subphenotyping of COVID-19 patients so that we can develop targeted treatment, and also predictive modeling of like one of the most recent paper was about using routine blood tests to predict if you are likely to be COVID positive or no, because the gold standard for confirmed with COVID-19 is the RT-PCR test, and the fastest RT-PCR test takes about 2 hours. It needs a special agent, and which is not that widely available. So, the regular RT-PCR test that takes 24 to 48 hours, so it takes some time. So if we can use some information like the routine blood tests that are fastly available and also more widely available in different regions and places to predict what is the potential risk of a patient having a positive COVID, then there is a more likelihood that the clinicians can get better decision support and understand what would be the need for how to allocate those, let's say, special agent, or the need in the resource in the hospital so that can get everything better managed. So those are just some examples. I think if, I myself went through the pandemic of SARS about in 2003. And if you compare like 20 years ago and now, you see there's lots of change, huge change especially on the data science side. For example, now you can see the numbers changing every day in different places where it's impossible to see 20 years ago. And also you see all these fast drug discovery in triggered clinical trials, which is impossible for 20 years ago. And all these already demonstrated huge potential and success of data science and AI type of models in helping with the pandemic. But I think it's just the matter. I mean, we really need to work with the domain expert to understand what they need and the actual problem instead of developing our model on our own. And I think this can make more and more model helpful in the actual fighting of the pandemic.
Right. Thank you so much, Professor Fei Wang. So I think I will direct my next question to Professor Yang-Qiu Song and let Professor Fei Wang to check the chatting room to deal with the further questions. Hi, Yang-Qiu. Are you there?
Hello, can you hear me?
Oh, yes, yes. So my question is, I mean, in this pandemic, we are faced with, astonishing human endeavors. We can see a lot of scientific papers published in a very fast space in Nature, Science, Archive, Bioarchive, and so on and so forth. I mean, which are already beyond the human, the capability to deal with this knowledge. So it is your time to use your, so can you show your perspective on how to use knowledge graph and knowledge graph mining techniques and to deal with this COVID-19 related papers to tackle the COVID-19 pandemic? Thanks.
Okay, I think there have been already a lot of work on this direction. Like as I introduced, there is a UIU's team, there is a UT Austin team, there's a Berkeley lab team. I believe there will be more. I myself, I will lead a small group of students working on this direction. So basically, I think there are many challenges. The first one would be related to the question, which is the trustworthiness. So basically, there is a lot of paper or just manuscript published at the internet. So we don't really know whether we want to trust them. Like sometimes we need to really do some fact checking based on existing knowledge bases to see whether the published papers are reliable. So then we can extract more knowledge from that paper maybe. Second thing is, I think there's still a lot of ambiguities in text. So basically, I don't think current NLP results would be really reliable to construct very high precision knowledge. So sometimes you need to sacrifice the recall to make the precision even higher. So basically, maybe you can build your knowledge base based on more frequent facts that you can extract it from the literature. So in this way, I think usually the knowledge graph you extracted are not complete. So that means you probably need to use your knowledge graph as an assistant to maybe acquire more knowledge from the text. So there's another trend in NLP that treat the text base as a huge knowledge base. So basically you build a huge knowledge language model based on a lot of text, and then you simply retrieve something from the language model instead of the structured knowledge base. So I think this is a kind of an implicit knowledge. Compared to the explicit one, I think it could be very powerful in terms of the language model could memorize a lot of facts or evidence or simply words or sentence. On the other hand, explicit knowledge graph would provide you ability do maybe a higher order inference, maybe multi-hop reasoning, or whatever that make it explicit and explainable to human beings. So to reflect your question, I think there's still no principled way to build a knowledge graph. As you can see, different teams are actually building their own knowledge graph differently, quite differently. Some of them treat the entities as the backbone, and some of the others treat the relations as the backbone. So, and then you enrich your knowledge graph with different kind of information, right? So I think that's good because like different teams would contribute differently. On the other hand, I think maybe in the future we need a kind of like a unified way of constructing this kind of knowledge bases, and then maybe we can like unify them into a kind of a bigger one from different organizations or institutes. In fact, I think the federated learning is a very interesting idea where you don't necessarily need to share your like knowledge, like your nodes or entities relations in your knowledge graph. Instead, maybe you can just share some node embeddings to others, and then you can conduct some federated learning over knowledge graphs to maybe improve your own knowledge graph, right? But this does not apply to COVID-19 because COVID-19 is quite open. Like people are kind of very open to share with each other. But like if you consider some other knowledge graphs, maybe based on like clinical notes or EHR data, then maybe that's more sensitive. In that way, maybe you want to share like node embeddings or relation embeddings instead of the node themselves. In fact, we have done a federated knowledge graph embedding work, which was submitted but not yet accepted. I think this one would be a very interesting direction to go. So I think that's probably answer your question. There is another question from the chatbot that is related to me, like the first one. Goes to network embedding and KG. What do you think is the next trend in this domain, either in application or algorithm perspective? Okay, so I think for the from the industrial perspective, I believe automating the knowledge graph construction would be a very important way to go. As I mentioned, there's no like unified way of constructing a knowledge graph. So whenever you have a new domain, whenever you have a new problem like COVID-19, you probably need to look at the data again and have a lot of dirty work to process the data. So that's very painful, I think. So basically, I think like building a knowledge graph construction tool, maybe on the cloud, automatically extract information for different customers would be very interesting direction. Like from the algorithm perspective, obviously there is quite few training data for different tasks. So I think there could be a lot of like algorithms like borrowed from other domains applied here. Like we can use meta learning to apply to different tasks. We can use transfer learning to transfer the general knowledge, graph construction like model to the domain specific ones. Or maybe we can use like federated learning, or maybe whatever like popular learning algorithms to this particular domain. In fact, when I review those knowledge graph extraction related papers, I indeed saw a lot of papers somehow just borrowed the newest ideas of deep learning and then apply it to this domain. And then I think they got quite good results over the tasks compared to the previous baselines. So I think this is very interesting domain and it's very useful. So in terms of the algorithm design, I think there's still a lot of things to do. Okay, I think I just reflect all the questions here. Thank you.
Thank you so much. So, and there is another question direct to Fei. Hi, Fei.
Yeah, I see that question, and I think Yang Qiu's comment on the first question was pretty good. And one thing I also want to add is that we see actually there's especially in medical informatics, there are lots of clinical NLP folks. And we also see clearly in computer science, including data mining, and of course we have our own NLP communities, ACL community. But a lot of the times you don't want a surprising, if you check the people in the two community, you will find surprisingly actually the overlap is not too many. So I'm thinking of, because recently I have been working on some knowledge graph related stuff as well. So I'm thinking of what is the gap. Actually, we develop as a computer scientist, data scientist, we develop a lot of good algorithm or knowledge graph or basis, but it doesn't seem they got widely adopted in biomedicine yet. And also in biomedicine, there are lots of, classic knowledge bases that are really widely adopted in different kind of biomedical problems, but most of them are not originated from computer science society. So I'm thinking of to the future. I think this is also related to the second question about the trust of AI in biomedicine. I'm thinking of the close collaboration between domain expert as well as the data scientist or the algorithm expert is, I think, definitely a very important way to go. And in order to get, I mean, of course, knowledge graph or algorithm, data mining algorithms is just one aspect of AI, but in order to get all those AI algorithms trusted that the domain expert, the biomedical researchers, the clinicians really would like to use or trust to use these, I mean, an effective collaboration and also validation, evaluation type of strategy is crucial. So, I mean, I think a lot of us are focusing a lot on developing novel algorithms, but how can you get the results of your algorithm or the model you developed really validated in real clinical scenario or biomedical scenario is a big gap, I would say, for especially for the computer science works. So of course, I mean, it is a general problem. I mean, the FDA is also working out white papers on how to get those algorithms or softwares validated or evaluated, because they are not like medications or drugs. So some proposals like treating software as a device, and somebody said, no, it is not a device. And there are lots of debates. And I believe this is a very important topic to work on. It could be technical, it could be really ethical or not technical, but this is an important gap in the whole loop from algorithm to real biomedical or clinical applications to close. So I'm thinking of this would be a very, very important topic that needs both the domain expert and as well as the algorithm expert to work on collaboratively.
There is another question. So in COVID-19, the data turns out to be more helpful are genomic and functional genomic data captured from patient tissues, an area specialized by bioinformaticians. How do you think you may compete or cooperate with them to make this type of work relevant to address practical questions? Haifei and Yangxiu. Maybe you can have some comments or.
Yeah, I see it is from Jake. I think this is an excellent question, and definitely this is not a competing relationship. I think definitely we want to cooperate. I mean, for me, for example, although I work a lot on the clinical data, but I work closely with the bioinformatics folks as well from the Cornell Precision Medicine Institute, and because from the proposal of precision medicine, I mean, this integration of genomic information as well as the clinical phenotypic information is emphasized more and more. And for COVID-19, we have, I agree. I mean, the two types of data has a lot of different aspects. For example, the genomic data is typically much more clean. The clinical data is usually much more noisy and much more, I wouldn't say complex. Both data types are complex, but the clinical data, we usually say it is much more dirty. And for COVID-19, there are already a lots of good works, very high quality works on the bioinformatics, the genomics, as well as the drug design based on the genomic data analysis, while at the same time, another line is there are lots of clinical discoveries about the COVID-19 patients. All those different clinical characteristics like the hyperinflammation, the multi-organ dysfunction, and so on and so forth. And from the genomic side, we know that SARS-CoV-2 is a host virus. Is a virus causes disease, and it binds with a lot of proteins, and you have a lot of expressions. But on the other side, how this gonna lead to those different phenotypic manifestation? People are still studying that. So I'm thinking of these are just the two different aspects. If you think about it from a network perspective, so these are just the information characterizing the health condition, the patient health condition from a different aspect. You can think of there is a good figure from the Science Translational Medicine about explaining precision medicine, where it says, the real goal of precision medicine is integrating those information from all different levels, from genomic, cellular to clinical, environmental, and so on and so forth, all those factors. So we really, to achieve the ultimate goal of precision medicine, we really want to find an effective way of integrating all those information from different levels of granularity. I think that is the way to go to achieve really the success of precision medicine. So that is also why this graph-based analytics is important, because it provides a natural way of considering both the entities as well as the relationships. I'm thinking of so in the future, really, the collaboration between, I was emphasizing like the collaboration between the domain expert and algorithm people, but also from like the bioinformaticians and clinical informaticians, and also data scientists. It really needs the collaboration of people with all different backgrounds to understand the disease better and design a better treatment plans to fight the pandemic.
Well, thank you so much, Fei. And we think we are running out of our tutorial's time. So do speakers have more comments or perspectives? And if not, do anyone has more questions? If not, we will conclude and end this tutorial. Hi, Fei. Do you have
Yeah, I would like to basically first thank you for everyone who attended our tutorial. And we welcome, as Chengxi has put all the relevant materials as well as the videos on his website, the slides. So feel free to view them and also shoot us an email, whatever you want. For discussions or collaborations. And another thing, I think, last thing, it's more of like an advertisement. So we have also a workshop on applied data science for healthcare tomorrow from 8 to 5 Pacific time, where, the theme of this year's workshop is actually trustworthiness AI in healthcare. And we have some prestigious speakers, including Jian Hu from IBM Watson Research, who is the director of the Computational Health Center, and also Hamza, who is the faculty at UPenn Wharton Business School, and also Peter Walker, who is the program manager from DARPA Joint Artificial Intelligence Center. I think he is also going to talk about some of the recent works on how the DARPA fighting with the pandemic. And actually at the end of the workshop, we're gonna have a COVID related panel where we have 5 excellent panelists, including 2 clinicians who took care of COVID patients at the front line during the peak of the pandemic in New York City. And we have 2 excellent informaticians talking about the informatics resources about the COVID. And also we have Dr. Chuan Gu from UCLA talking about his work on integrating machine learning and epidemiology models to predict the trend of COVID-19, especially in the Los Angeles area. So everybody's welcome to attend our workshop tomorrow.
Oh yes, I just share this web page. I don't know if you can see in your screen. So this is the web page of tomorrow's workshop, just as Faye said. So this is the information of this workshop. All right. Hi, Yangqiu. All right.
I have no more to add. Thanks.
All right. So thank you. Thank all the organizers. Thank you, Faye. To organize such wonderful tutorials. Thanks all the audience. Thanks for your coming. And thanks for your questions. There are so many wonderful questions. We just copy that and copy these questions and we have a really nice discussion with all the speakers in this panel and Q&A session. Thank you so much. So we are running out of time. So thank you. This is all about our tutorial. Thank you, everyone.
Thank you.
Thank you.